just like that, but then I got be about time. You're better than me. Far.
Well, good morning, everyone. We'll give everybody just a few more minutes to join us, and then not expecting this to go a full 3 hours, but it won't be too short. Let's see. Okay, give a couple more a chance to get on here. And also, so you're aware, I will be monitoring the questions. Again, I don't have anybody with me today because it's 4th of July and I give everybody the day off. So it's just me kind of controlling the whole works here. So we are going to cover, because I haven't recorded this yet, and I've done this course for the IEEE Dielectrics and Electrical Insulation Society for quite a few years. This will be the presentation part of it. It's a little difficult to do hands-on virtually, but we're getting there. We're working on it. Okay, so let's see. I think we have enough to get started. This is being recorded, so if you have to duck away for any reason, or I'm putting you to sleep, you can come back later and watch it. For those who have signed up and you stick around for the presentation, there is a certificate of attendance that is automatically sent, usually the day after. So expect it tomorrow or Sunday. This is going to cover primarily the electrical side of electric machines, although we will discuss bearings. All of the lessons I'm going to teach are how to perform simple and advanced root cause failure analysis. So I hope you enjoy it. If we have any problems with network, hopefully we don't. There's nobody in the office park or industrial park this weekend, I think. So we should have a pretty good connection. And there we got a good number there. So for those who are just attending, yes, I'll be monitoring questions as we go on, and I'll answer them as I can stop and answer them. I don't mind. You don't have to wait till the end. So if there's something that you're not clear on or whatever else, I do have a copy of the very old version of ProAct on my system. So in the end, we're going to go through and just do a quick once over. I'm going to show you some resources you can access. This is not a sales pitch. This is actual training. So we are going to also discuss some new discoveries that we just published 2 weeks ago at IEEE, and we'll be discussing again. I traveled this Sunday out to an EPRI conference to talk about electrical and current signature analysis, including some new methods that we use and some new discoveries that have been made. So I will cover those in this presentation and may even pull up the IEEE presentation if it makes sense. So with that, I'm assuming everybody can hear me, and we'll go ahead and get started. So my background, Howard Penrose, for those who don't know me, I've been in the industry now, I can officially say 40 years. So 40 years means I've been in a long, long time. I started in the US Navy as a motor repair professional and industrial electrician or electrician, and have continued to be in that industry through till now. So I've run motor repair shops. I've been a winder, a mechanic, a machinist, pump mechanic, basically everything associated with electric machinery and then some. I've been involved in the US Department of Energy programs such as Motor Challenge, Air Challenge, Steam Challenge, the works, and then worked with that to fund it through separate business. And then finally adopted all of those technologies at General Motors in the mid-2000s. And this was following my running the Energy Resources Center at the University of Illinois at Chicago. So I've been a consultant, I've been a motor designer, I've been, you name it, I've been in hybrid vehicles, I'm in industrial work, the works. I'm seeing that there may be some problems with, there we go, the system, so we'll keep an eye on that, and I will slow down as I see that occur, so we're coming back up to 100%. So right now, my my responsibilities include IEEE standards. I am the I'm the generator and electric machine representative for the U.S. for Seagray, and I'm the chair of standards for wind, solar, and energy storage. So that's kind of my background. There's a lot more to it. All kinds of certifications, big background in machine learning and AI. So stuff like that. That's probably the only, well, actually we'll probably use the term AI a little later because I'm going to show you some tricks that I use on occasion. So let's get into the guts. Yes, the fun part about root cause failure analysis is we are chaos engineers. Now let's get out of the video stuff because apparently that slows the thing right down. This is referring to the last set of case studies that we will do. Just to put this into perspective, I've done a lot of work in the past several years, past 20 years, I should say, in wind and wind power generation in particular, as well as some solar stuff, but wind primarily. So this is a fault we will discuss. This resulted in a paper that was actually incorrect. A series of papers by some motor manufacturers and others because they made assumptions, and we're going to cover that in a minute. This was a breakdown through 2015 and what was believed to be the primary issues with generators. What it was the observations of a single motor repair shop, which meant that basically that it's just the observations of a motor repair shop. So bearings, they're all ball bearings, so they always got replaced. So all of the repairs had bearing issues, of course, because those were replaced. Bearing issues are not that severe in the wind industry ever since some corrections were made in far as insulating them and so on. Stator wedges, those were an issue. We'll talk about that at one point. Rotors, that's the big one. That's the one we've just recently solved for the industry. That's what I'm presenting on at PES at the end of July, Power Engineering Society. Wiring failures are the rotor ones. This is the catastrophic end of it when it just lets go and basically the winding takes out the stator. This is a fractured wiring. So when you hear me talk about it, that means that's the connection for the rotor winding. These are wound rotor machines. And when I talk about the gears and the gearbox, so this is one that we had detected. This is a planetary gear, and this is the ring gear for that planetary gear. They're quite massive. So we're going to come back to this later and so on. Main bearing. This is actually the study we just completed. You'll hear a term called relative harm index coming out soon. That was the paper we just did a few weeks ago based upon a multi-year study that involved the Department of Energy and others. Okay, so let's see how this works. Just so you understand wind turbines, this is the yaw deck. Just below here, that is the yaw with gearboxes and AC motors, generator, gearbox, main shaft, and then it all attaches to the hub. The hub actually sits and puts strain on that main shaft, so that is all connected to that. There's all kinds of protections in place, and then inside here, and in most designs, they're DC motors. There's the pitch motors. These will tilt and pitch the blades. There may be some hesitation going on. Sorry about that. I'm seeing some delays there. So that's for when we get into that case study, because I'll be so into what I'm talking about that I probably will forget to mention terms and construction. So let's get into the concepts behind failure analysis. And I'm experiencing some of what we'll talk about here right now. But let's start with this accident. This is outside of my condo, which is way off to the right. But in any case, an elderly lady owns this vehicle, and I went out for a walk. It's literally this is from 2018, I want to say, and they had made her start parking outside because when she parked in the garage underneath the building, she had this habit of jumping the barriers and hitting the gates and stuff like that. So they said, you have to park outside. So one day I'm out for a walk and I see her car here. There's the parking lot here. So somehow it jumped that and came crashing down here. And by the way, this is all roped off over here, right about where I'm taking the picture. There's a group of people all talking, all of whom had just stopped like I did, but all of whom had seen and observed the accident, as in they weren't actually there, but they all in their minds had actually observed it. And several of them who knew the story of this elderly lady said, oh yeah, she just did this and that and everything else. So I took a picture of it, moved on to where I was headed, come back later, and I find out that what really happened was her son had parked her car for her, and he had put it in reverse, and there was a problem with the transmission, so mechanical failure, and when he went to back up, it went forward instead, and he reacted badly, and that occurred. So everything that had actually happened was not the equivalent of what people were saying. And this is really important because the other example, what I'm going through right now, we're talking about why equipment failed in Spain. This is a CGRE and IEEE discussion, why they had the outage. Well, everybody's pointing the finger at renewable energy. It might be, it might not be. But I got into the first presentation, and it turns out I was the only representative of that industry, and everybody else were in other parts of the utility industry and were making assumptions about how everything operated, and what they've read in magazines and what they've seen on TV. But nobody, when I saw the graphs, I went, wait a minute, what were end users doing that caused the voltage to do that? And they said, oh, that doesn't matter, it's because of this. And I said, well, but those controls counter that by doing this. No, they don't. Yeah, they do. That's an actual IEEE standard that you guys wrote. So, and I know it's in place. So that was part of it. There's ways to get around all that stuff, but that's what had to be investigated. But instead, the view was immediately that that was the problem. They had to make additional corrections to the new technology in order to fix it. But if they don't actually find the root cause, they may not actually fix it. So we need to verify that. The actual research, the actual study by the utility there isn't finished yet. They had an academic on there who knew something about it but wasn't involved. So it's very, very interesting. So we have that meeting. I wasn't going to be there on the 27th, which is a Sunday, but now I am. Because I want to make sure that the working group on that paper that's going, or the report that's going to come out, actually does some form of RCFA. And that's a big part down towards the bottom. And I'm going to explain why, we're relatively popular in solving problems. That's the reason why is I make every effort to not have preconceived notions, although I'm human and I will, right? But it takes 7 to 11 errors to generate a failure. This is a fact. This is a big part of reliability engineering. So in there, there's going to be, that's part of what I call the chain of bad, or the failure chain. And what we need to do is figure out how to break that chain. It all becomes an effect, cause, effect chain. It could be a decision that was made in manufacturing something. It could have been bad training. It could have been, anything else that's going on. What we do try to teach in RCFA is avoid pointing the fingers at a person, because, and that's, pilot error. That is the worst possible thing. They use it in the news all the time. But if the pilot's made an error, something along that chain allowed that error to occur. That's not the root cause. So what we often find, though, is root cause failure analysis is limited to the obvious. I even just bought the latest copy of one of the motor repair industry's RCFA booklets, and it's basically, oh, if you see this going on with a winding, it's a winding short, that's the root cause. Bull, it's not the root cause. Something generated that. The most common problem I find in an RCFA are the engineers, and people that have a stake, meaning that they have a responsibility, or they're worried, or they're protecting things. They often will jump to conclusions. Now, if somebody calls me and says, hey, I've got this problem on this machine, I'm going to jump to conclusions. It happens all the time. It means that about half the time I'm going to be incorrect. And I understand that. And I say, well, it's most likely this, or it's, in my experience, it's been this. Give this a try. Let me know how it turns out. Then we'll go the next step. Closed minds. I've seen it all the time. Steel plant near here, we had a situation where they had the motors failing constantly for about 7 years. And this is normally what we get called into, is this stuff that's been going on for months or years. And everybody was locked in on what was going on. So we had the operators trying to work around the VFD, or the drive controls, the OEM who was monitoring the drive controls, modifying the drive controls to stop the operations guys to do that, and the maintenance guys pointing at the operators saying, hey, they're using a crane to pull up on something to increase the tension on the steel rolls. So when I arrived and I went to the repair shop and I got a look at the records, I saw that 7 years before, all 4 of these DC machines had basically stalled for several minutes, and we're getting full current on the armature. And so I looked through the records again, and I was wondering, hey, is it possible that that they didn't replace the commutators, which they had not? So I knew that they had annealed the bars in the commutator. So that was going to be part of the issue. So we identified the problem pretty quick. But we had another issue, and we had an issue of infighting between the groups. So we used the RCFA process over about 2 weeks to try to get operations back in order by bringing the groups back in line and focused. That meant that, we sat there and we said, what are the possible causes? And the thing about the crane came up. So we got up as a group, walked out there to look and see that there was literally no crane within 100 yards. So that, of course, was possible. The other thing is poor training in RCFA. I mean, we as human beings want to say, yep, that's it. We watch the news, we jump to our conclusions based upon the inputs we receive, which is programming. We're getting programmed to have certain reactions. It's just like whenever I see the 51% of all failures are bearings, I've actually seen the studies. I know that is exactly not what the studies say, but because of commercial articles and magazines that have leaked over into technical documents, we all make that assumption. I've written about it, and people specifically will read my papers, and in their heads, they won't see what I'm saying because they make the assumption based upon decades, since 1980s, decades of seeing these articles by authorities that make these statements. So you have to leave that behind. One of the other things, just a note on RCFAs and my approach to them is if I get called in to do an RCFA or troubleshooting at a site, and I walk in there and they haven't solved this problem in months or years, and they start directing me on what tests need to be performed, I send them a bill after I walk out. And I tell them, when you're ready to actually solve the problem, bring me back in, because there's a process. And if you skip the process and you allow somebody to direct you in the process, you're going to fail. You're going to end up with the exact same results as they did, and then everybody can go, see, it's not solvable. There is not a project that we have been brought into that we have not solved a problem. Last Monday, we were called to go down and take a look because there was this huge issue with this energy project at a hospital. And I walk in there, and in 15 minutes, we figured out what was wrong for months. They forgot to look and see and make sure that the electricians connected the systems properly, and they had not. Basically, they'd put in filters and shorted the filters to themselves. So there was zero impact on that process. So now we're into a project now where we have to go back and fix all of it. But they were trying to tell us, oh no, it's this, oh no, it's that, or oh no, the project didn't actually work, when it just wasn't installed correctly. So these are things that you have to keep in mind and keep an open eye on the stuff. Now, are there standards? Yes, there are standards for performing analysis. I believe there's IEC standards that are equivalent as well. I tend to stick with IEEE for the most part. How did they forget? Yeah, good question. Yes, what they did was, instead of, they brought in a group, and I had been contacted the early part of the project. I said, that's the wrong group to bring in when their people are failing drug tests on site, stuff like that, as subject matter experts. And their subject matter expert bit was the training they received from somebody who hadn't been trained. So the part of the solution to the root cause failure analysis, which we just finished that call yesterday, is in the future, anybody who goes on board, we're developing a training program for this particular thing. Will have to be a subject matter expert, will have to have had 3 days of training and have been on 2 projects and signed off by the manufacturer. So basically 3 steps before somebody's considered a subject matter expert. Well, of course, all the people involved in the money side are screaming about how much that's going to cost. And I said, well, on this one project, how much did you spend? And they spent 3 weeks, 3 5-day weeks with 4 engineers on site that were not cheap, a large group of electricians, and basically having to do live work because it's a hospital, and in areas where it would affect patients. So I said, how much did that cost? And they told me, and I said, and you understand we're doing all of that work again, except this time it costs you to do that. What it would have cost for us to bring those subject matter experts into a classroom and train them for 3 days. And then have somebody from the factory on site verifying that they're doing it correctly for the on the job part. It was, that was the big part. So it fell down on training and financial decisions and a couple other latent issues. And that's usually what it comes down to. Something was skipped, and there was some kind of reason for it. So anyways, getting into the standards. This is obsolete right now. I want to say it's been administratively withdrawn, and there's a reason for that. 1415, I was the secretary for it. We sorted it out. We got it done. That standard is, see if I can drag it over. It'll sit on top. There we go. I'm running with multiple screens today. That's this one here. Now, it was published in 2006. Everybody who had a technology jumped on board with this standard. So the first part of the standard is, I like to call it very commercial. I'm partially guilty of that because we were watching, I was with a company called Alltest at the time, and we were watching all of that going on. There I am. And by the way, I'm involved in a lot of standards. So when I get into arguments with people, I can flip over to the acknowledgements and say, there I am, where are you? It was a joke. But in any case, the purpose of this standard was supposed to be this last part here, how to perform a failure analysis. And what it ended up with was this first part here, which was 4, which is basically everybody's technologies. So everybody who hadn't been mentioned in technologies was suddenly mentioned in technologies. So it became a dumping ground. So some complaints came in primarily from competitors that were in the list. So in here, if you look, you'll have surge testing, and you're going to have PDMA, and you're going to have all these other different troubleshooting things, and you're going to see that some of them say potentially destructive. And yeah, here's current signature analysis, and voltage signature analysis is in there as well. So it has electrical and current signature analysis. The vibration guys didn't like that. That's an ongoing battle that's been happening. Surge testing is in here as well. Where is it? Surge test here. They did not like this. The surge test companies did not like this. And then this is an interesting reference, IEEE standard 522, because it is meant for coils. It's not meant for complete machines. There is no IEEE standard, or there's only one IEC standard that covers, let me correct that. There is IEEE 1068, which is out for comment right now. That's what I'm going to be doing after I get off here. Yeah, because there is no increase in losses, but we want to allow a 20% increase in core losses through a standard repair process, which works out to between 0.5% and 1% reduction in efficiency in a machine. But yeah, that's the battles we fight. Anyway, so all of this had gone on, and there were a couple of complaints in there because, the high voltage guys didn't like the low voltage guys and everything else. And, people were saying, oh, it's about, about form wound motors, and somebody else says about random wound motors. And it isn't. It's about electric machines in general, and it covers all of them. So in any case, we allowed it to retire. So in 2018, there was no vote to remove it. There was just no vote to continue it. So they do what's called administrative withdrawal. That means it's still available. You can still buy it. It says withdrawn on it, but the only reason for that is because they couldn't find anybody to continue working on it. So IEEE 1415 has been restarted. Now, I was supposed to be on the original one, but because of IEEE politics, I got accidentally left off of an email. So I am going to find out what the heck is going on when I'm at the meeting in the end of the month. So I will be back on it. So, but in any case, it still exists. You can get your hands on it. That's a good one. Another one would be the EPRI documents. Now, EPRI, oh my gosh, their stuff costs $25,000 for this and $50,000 for that. Nope, you go to EPRI.com, you sign up for an account, and a lot of their stuff, if it's older than 10 years and it's not sensitive nuclear, they make it available for people. So these are available for free. So make a note of it. You just look up troubleshooting motors and it'll be there. And then this one here is evaluation tools for electric motor testing, which covers most of the technologies, except they're wrong about a few. which is why I'd share the thing for electrical and current signature. Like, for whatever reason in the 1990s, and I know exactly who it was, and I know what tool they went with. They convinced EPRI that electrical and current signature analysis is only for rotor bar testing. So we, just so you're aware, we in 2020 and 2020 through 2021 were involved in a project with AMS out of near Oak Ridge National Labs. And I went in and trained them and showed them that actually it is to test the entire system. So the newest documents, which are 25 grand each, say, oh yeah, here's everything you can do. So we're now doing a C-grade version of that. And that one will cover all technologies. And I think I've got like 2 spots left for the team that I want. So that's on its way, but this covers all that stuff, and including the troubleshooting guidelines for each of the type of tests. Now I'm not gonna close this out. We'll come back to it at some point. But let's say we have okay, so there's also some new standards coming out. So this will be wrong because of the age of this. But if we come in here and it'll say, okay, resistance greater than 3% between windings, test for resistance to ground, return to serve, da da da. And so then it comes down here. Oh, I'm sorry, that's the previous one. Polarization index testing. It talks about the PI test and everything else. What we are coming out with, and it's and they only go through the PI ratio, not the insulation resistance profile, because and here's the decision tree based on polarization index and so on. The IEEE P, which the P stands for PAR, meaning it's in development, P97 is advanced DC testing, and it's going to cover polarization, depolarization testing for large machines, in particular hydro and large service generators, and then also the insulation resistance profile, which is basically how to map the curve and make decisions based upon that curve. And if we get a chance, we'll come back to that later. I believe I have some slides associated with it. It's in the works right now. A gentleman, Dave McKinnon from PDMA, and I are the leaders on the IRP write-up. So that will be there. So those are those 2 documents there. And for transformers, C57 125, I used this a couple of times for evaluating things like mobile transformers and so on and so on and so on. Great tools, and it always helps to be able to use those to give you some traceability. So those are the things that I would use as part of the RCFA, but not the RCFA. We'll get into that. So the first one is a simple 5Y. Now, why is the 5Y important? It's important because it's something I can do on the shop floor, on the spot. It causes critical thinking to occur, and it doesn't have to be a straight line. There can be parallel lines coming off of a 5Y, meaning I don't have to go, why did the motor fail? Electrical or, was it electrical? No. Okay, must be mechanical then. I can have, was it electrical? Was it mechanical? Was it whatever? And I can come across and say, okay, it's one of those, and I can continue down and turn my 5Y into a tree, which is part of the way towards the type of system we'll talk about. So what are the benefits of a 5Y? Focuses the attention on the best areas to address, meaning it focuses you on having to provide evidence. All of this you're going to hear from this point on. I'm going to talk about evidence-based testing. Why is that important? Well, I have taken PROACT analysis, which is the advanced version, into courtrooms. Well, I haven't even had to go to the courtrooms. We've won the cases usually in deposition because I identify everything in their side and my side, whatever side I'm on, because I'm an expert and supposed to be neutral, but basically everything in the that could go wrong or could cause that particular thing, and then I have to show the evidence for that. So you want your RCFA to be strong enough to stand up in court. It could be to stand up in front of the C-suite, could be to stand up in front of the manager, could be to stand up in front of a customer. But in any case, you want it to be strong enough to do that. A 5Y, on the other hand, that's something where if I'm troubleshooting something, I'm going to do a process real quick. Okay, so it focuses the attention on where to address the issue. Is it a short-term or long-term issue? Identifies, analyzes, and eliminates the gap between the current situation and the reliable operation. That's the real goal. Reduces waste, works on effective communications, creates a problem-solving environment, and reduces repetitive failures. We implemented this at General Motors, and we put it across multiple plants before 2009, when everything happened, 2008, 2009, and it was phenomenal. We had, by the time people came to us with problems, they already had recommended solutions. So it was great, from the electricians and mechanics all the way up through management. So the basic process, identify the problem. Now, the identification of the problem is the toughest part of an RCFA, other than finding some data or arguing with unruly managers who want it to be something that it's not, okay? So identify the problem. Is it a repetitive issue or is it a one-time? Did it just happen for one time? If it's a repetitive issue, you might want to push it out to a more advanced study. But if it's a one-time failure, you can figure out, was it an untrained operator? Was it, we're pushing production up too fast? Things like that. But you start out with something as simple as motor failed. You do not say motor winding failed. You do not say motor failed because of loss of power. Those are the conclusions. Motor failed, because you don't know what actually, that might be the triggering event, but that's not the root cause. Identify the problem and at what level. So plant shut down, and then you start to figure out why the plant shut down. Understand, collect data in order to provide evidence and impact. So even under something as simple as a 5Y, preserve everything you can, any data. It's phenomenal. Unless you're in a plant that doesn't allow cell phones and pictures, a lot of plants I go into, it's like, you cannot have anything with a camera on it. And you go in there and you say, well, I need pictures of this, that, and the other thing. So they go get an approved camera. So that they can sort through and make sure that the information they're providing you is not something that could cause them problems. Okay, so there's that. Or just like when we were down at Buckingham Fountain doing verification the other day, they're like, take all the pictures you want. So, we were taking pictures of the problem, pictures of each other, for LinkedIn, stuff like that. Understand, collect data in order to provide evidence and impact. Identify the possible factors that caused the problem and the root cause, meaning what are the possible things that led up to it. So plant went down. Electrical power, did it go down because it was electrical power? Did it go down because of weather? Did it go, so you start listing those, weather, power, blah, blah. And then you start figuring your way through that. Could it have been that? Well, no, the weather was nice and sunny and perfect. It's exactly everything we wanted. There's been no thunderstorms in the past several weeks, so no, nothing there. And then you go, okay, well, lost power to the plant. Okay, yes. Okay, why did we lose power to the plant? In that case, you're then picking up the phone and talking to the utility. And if you talk to somebody and they go, oh, well, yeah, it was this happened and that happened. Okay, great, send me the records. Oh, no, I can't do that. Well, yes, they can. Because every time I've asked for it, I go, bull, you're required to by law, give me the records. So they give me the records and there we go. And you can find out. And I've had that happen twice. Determine a corrective action. How can you solve a problem from that corrective action? And what are the impacts? and that's that monitoring the system to confirm the finding. One plant, we had identified a failing 69 kV line from the utility. It was a dedicated line to the plant. We did the root cause. We figured out what was wrong. We had them switch over to another 69 kV line, which also serviced the local community. So all of a sudden they had power issues all over the place coming into the plant. The plant did not have corrective equipment in place, and they lost several drives. So we were able to then use that RCFA to go back to the utility and get a shared cost on the replacement of the drives, all by using RCFA data and evidence. Because we had the details, there was no battle, there was no fight. There was, oh, okay, here you go, because we don't want to spend time in court, basically. So root cause, why? Because. Why? Because. Why? Because. That is your effect. Plant went down because, well, why did that occur? Because, why did that occur? Expect you to be between, by the time you're done, if you're at the right level, you should be between 3 and 7 points. There's some that are very, very quick, you know. Machine failed. Why? Well, operators flipped this switch. Why? Operator wasn't trained. So, you know, it can be as shallow as that. Well, I mean, it goes beyond that. Well, why wasn't he trained? So why root cause analysis? It is a method used to address a problem or nonconformance in order to get to the root cause or fundamental reason for the problem occurring. It's also used so we can correct or eliminate the cause. Most RCFAs, if we're going to an advanced RCFA, will pay for themselves in terms of days often. It means it's a big problem. It's been there for a while. Here's how we correct it. Traditional applications identify the causes of operational failures. Resolution of customer complaints. We use that here for customer complaints. I'll get something in saying something's not working right in a software program. So we'll take it in and we'll run through and we'll say, okay, the end user didn't do this step in our process. Well, why didn't they do the step in the process? Was it training? Well, we don't count on that. We say, okay, how did we allow that person to miss that step in the software? What do we do in the software to prevent that from occurring again? And is it a consistent problem or is it a one-time issue? So then we are able to make those modifications based on a decision, based on data and facts. Disposition of non-conforming material. Basically, if the problem goes back to a problem from a vendor, what happened with the vendor that caused that? And sometimes RCFAs can go right into a vendor investigation. We had a whole bunch of motors fail when I was VP at a repair shop, and it was right after that whole period in 2008. We had a lot of people unemployed. All the wire manufacturers were coming back up into operation. We went over and discovered if we bent the rectangular wire from that particular facility, it would flake. Well, that meant that they overcooked it. They basically when they went through the curing process, there must have been a problem. So we took a trip down to the wire manufacturer. They had the wire drawing area and they were doing a pretty good job there. But when they went to the spot where they were putting the enamel on it, and I talked to one of the operators, said, oh yeah, we replaced everybody. I'm from the old group. I don't like how they're having the temperature increase. So we used that in a discussion to go over and look at the records. And sure enough, they increased the temperature of the process by 5 degrees centigrade, which was apparently enough to, for the length of the oven, to overcure the material and cause it to delaminate. So, there's things that can occur like that. Corrective actions, plans resulting from internal, external, and customer audits. So you come up with a corrective action plan. Usually a decision has to be made. If I'm going in to do an RCFA as a consultant, in the end, I'm presenting a report to the customer and saying, okay, you have a financial decision to make. Here's the evidence behind that financial decision. Here's the impact of that financial decision. Is it going to reduce cost? Is it going to cause other problems, et cetera? Sorry, allergies have been really good around here lately, so pardon me if I'm coughing or sipping. So root cause, how? Use a specific set of steps. Now, this is 5Y or anything else to find the primary cause of the problem. Sometimes we've gone back to an RCFA, and this is why you need to make sure everything's recorded, and say, oops, we forgot something. Determine what happened, determine why it happened, figure out what to do to reduce the likelihood. RCA assumes that systems and events are interrelated, meaning that there is a cause-effect relationship. An action in one area triggers an action in another, and so on. So basically, we are saying there's a logical process to failure, that there's a failure chain. I like to call it the chain of bad. And you'll usually find the basic types of conditions. Physical causes, such as environmental materials, tangible material or equipment items fail in some way, meaning supplier-based materials or something that maybe you put together. I mean, if you're a repair shop, maybe somebody installed a bearing wrong, something like that. That gets back to other things. Human causes, people did something wrong or not doing something that was needed. Human causes typically lead to physical causes. This is that pilot error effect, because you're not supposed to end with Joe did this. You're supposed to end with Joe did this. Why did Joe do that? Okay, so organizational causes or methods, a system, a process, or policy. We're seeing a lot of that. I remember when the arc flash studies came out, and we lost a steel plant, and one of their senior managers lost his job because the safety department had put out a policy, and the plant manager had signed off on it that you were not allowed to open an electrical bucket for any reason whatsoever because of the danger of arc flash. That meant that you could literally not do infrared. You could not go in and verify things are de-energized. You could not open up a cabinet to make sure to actually replace a fuse. So they had on a main switch gear, they had it go down. It took down the plant more or less. And the manager finally said, you know what? I'm ready for retirement anyways. Open up the cabinet for the guys to do the correction. Because he violated the policy, it cost him his job. But they were back up and running. So when we get into a root cause failure analysis like that, it's like, okay, what idiot made that decision, right? Well, why? And then you get to, okay, safety department made that decision. Nobody from the reliability and maintenance department was involved in that decision-making process. Why did that occur? And then you go on, you're like, well, OSHA requires you to do an analysis, and you have to have all the stakeholders involved. So there was a problem with their process, and Environmental causes, temperature, light, and humidity. And these are not as difficult as you think. I use the NOAA databases all the time for all of that data. It's all public. I'm doing an energy study for that hospital right now. That's how we identified something didn't work. I've got other things, but I've got the kilowatt hours, and I'm able to go through the local airport through NOAA, NOAA.gov, and I get all the temperature history by day for that location, and then I can even see if there was thunderstorms or how many lightning strikes in the area, all that stuff. That's all public information, especially in the States. Root cause analysis looks at all of these and involves investigation of patterns of negative effects, and discovering specific actions, what led to that defect. Because often it only takes one change to affect that entire chain. Okay, so 5 steps to the resolution, root cause. Okay, so in this case, we're talking about 5Y. Step 1, define the problem. What do you see happening and what are the specific symptoms? Motor stopped running. Step 2, collect data. What proof do you have that the problem exists? Well, it's not turning. How long has the problem existed? What is the impact of the problem? Okay, so what if it's we're doing one now for a pharma company, multiple bearing faults. I could go a little further than that, but I want to say multiple bearing faults because we want to split the bearings and look and see what's going on. What proof do you have the problem exists? Number of faults discovered. How long has the problem existed? 4 or 5 years. What's the impact of the problem? Bearing fluting. Then we discover that as we're doing the investigation, we discover it's not just in the motors, it's in driven equipment and some other equipment that isn't even attached to an electric machine, let alone a VFD. So then we continue, identify possible factors that cause a problem. What sequence of events led to the problem? What it can basically, okay, it suddenly started happening 5 years ago. What happened? What other problems surround the occurrence of the central problem? So what happened at that period of time? Well, and we looked into replacement of drives. We looked at all kinds of other things. And one of the things that I kind of went, huh? And I said, well, what about that building next door? It looks new. Oh, it's a data center. When was it put in? 5 years ago. Oh, so we started to look at the ground ties and we collected data and then we traced it all the way back up to the machines that were seeing the high rate of failures and discovered that the harmonics that they were putting off into ground next door at a very high frequency were traveling into the other plant and were circulating currents. So that was the end of the 5Y. Now use the 5 Ys. Step 4, identify the root cause. Why does that cause exist? What is the reason for the problem occurring? And keep drilling down. Even if you go past 5 times, you started too high up, you're going to go past 7. But if you're at that point, keep going. Recommend and implement solutions. What can you do to prevent the problem from happening again? How long will the solution? How will the solution be implemented? Who will be responsible for it? What are the risks of it? Now, this is interesting here, and a lesson learned for us as well is often when I go out and, we'll go out and we'll say, why are all my machines failing that we put on VFDs? Well, where are the filters? What are filters? Well, you need to have filters on these drives. Well, they told us we don't need filters because they're clean drives. You always need filters on drives. So we took a look at the output of the thing. We saw that, installation was ignored. We said, well, basically, you're going to have to rerun the conduit. You're going to have to run new grounds, and you're going to have to put filters on it. Well, how much is that going to cost? Well, let's go get some quotes. So we get some quotes, and we come back and we tell them, and they freak out. Nope, we can't do that. Well, then, here's the next thing to do to reduce the failures, but it's not going to solve the problem, and you document that. Because if the problem continues, then they're going to start pointing, well, we brought in MotorDoc and they couldn't solve the problem. Well, no, it's just the management decided not to do it. So let's take a look at this fan system as an example. This is a real world example. My examples are real world. They're not something I just made up. So this actually happened on top of an automotive facility. This particular fan has an environmental impact, which means if it goes down, it costs them money. Either they have to shut down or they pay large fees, or large fines, I should say. Excessive noise from the fan system. That's the problem. Now we know that they've had to do certain things, but we're going to ignore that. It's noise. Well, I mean, that part's noise, but it is noise. So excessive noise from the fan system. Why? The bearings are noisy. Evidence? Oh, you can hear it. That's a legitimate. You can hear it. I have literally, that's a nice thing about cell phones. I've literally taken my phone, if I don't have ultrasound, and now I've got the visual stuff, but I'll record the sound. I can get up to 48 kilohertz on here, so that means that I have 22 kilohertz worth of data. So grab that. Why? Belt tensioning, we tested it. Belt tensioning was good. I bought a belt tensioning, little ultrasound one just specifically for it. They asked us to tension the bearings, tension the belts. We went up there and it's like, no, there's nothing wrong with them. They're exactly what's calculated for this application. However, we noticed something. So greasing, yes. Why? Improper grease used. Why? 3 types of grease needed for the application, only 1 used. Note proper greasing and types identified on the labels. Why? Electrician used only 1 grease that was available in the room on the other side there. Why? Improper training. They were using apprentices, people with no experience, because it was considered a lesser job. I mean, I remember when we still had oilers in the industry. Their sole purpose in life was lubrication. Why? Improper training. Why? Training for greasing not identified. They had no records of ever having anybody come in and do training. What's really wild about that is a lot of the lubrication companies will come in and do that training for free. So, why 3 types of grease needed for application, only 1 used? Note proper greasing and types identified on the labels. So the labels had the type of grease to use, all 3. So they had a regular bearing on the opposite drive end. They had a roller bearing that required a different grease on the drive end. And then the fan, its pillow block bearings required a different type of grease. So 3 different types of grease, 3 different base types. Okay, so so that one was the motor lubrication of Polyrex EM, and let's see, lube type Chevron Moly for that, and motor shift fan shift. And then there was another label for the drive end of the motor. So this is the fan, and this is all right in one spot. Well, if you're a technician, the manufacturer, oh yeah, we put a label on it. The technician, he's not going to look at that label. He doesn't have time for it. There's a lack of identifying methodology. So one of the things we did, was we initiated a color code system by bearing location and grease gun. So in some places we've seen it where they paint an entire end shield a certain color if it takes a different type of grease, and they match that color to the grease gun. Ensure all personnel who will provide greasing are trained. And they had a training area, but because these were, first year apprentices, they were sending around to do greasing, they didn't bother training them. So our feeling was, bring in the free training, and it's only a half a day, get the basics in, at least see what the impact is, and then you can go in for the full 5-day training program. Note that a specific individual was not called out by the RCFA. So we didn't call out an individual, never ever do that. They get defensive then and stuff gets hidden. A review of the success should be scheduled as part of the implementation, which we went back a year later for a different thing, and went ahead and checked on that, and they hadn't had any other problems. Okay, so let's get into the fun part. Just want to make sure, are there any questions on 5Y, or did I make it really confusing? But you can see it's critical thinking, and it's also, for a 5Y, it's also situational awareness, being aware of what's going on. So when I walk into a facility, I might have been in similar facilities before. I'm not used to that facility. I'm observing things. I'm seeing things. I'm seeing what looks out of place, stuff that people learn to live with. Human beings are very adaptive. I remember doing a chocolate factory, and we went in there and they had a glycol pump next to the chocolate mixer, which was open most of the time, in which the seals were failing. Well, you don't want to get glycol in with your chocolate. It kind of tastes bad. There's no reason to eat something that'll make you go blind. But in any case, the operator had turned in a couple of requests to have it repaired, and it was ignored. So he just forgot about it and became used to the sound. We heard it, and immediately identified the problem because of the situation. So let's get into a more advanced process. There are many, many, many types of these systems out there. ProAct is one of the early ones. It comes from Reliability Center. If anybody's heard of Bob Latino and them, if you've got on to me on LinkedIn, make sure to link up with Robert Latino or Bob Latino is his name. They've sold that off. That's now owned by another group. So Reliability Center, I think it's reliable.com or reliability.com. In any case, this process is available as an online tool now. They sell it or license it. I've still got an old version, Windows-based version that still works on Windows 11 and Windows 10. So the ProAct method stands for preserve the evidence. So the first thing you do is gather all the materials and evidence. Will there be a recording of the session sent on request? There will be a recording. It is going to go up. Yes, you will be able to get this, and it will be public. Preserve the evidence. Order. The investigators or team, meaning put together a team of stakeholders. Analyze the failure. Communicate the results, and then come back and verify. Now, the software is set up to follow each of these steps, and basically, just pop this up real quick. As an example, this is the example we'll take a look at later. I can build up equipment, facilities, the company resources, so I can build a whole library of RCFA studies and go through the chain and answer questions. We're going to do one of those at the end today. So in any case, do that. List the probable and improbable potential causes. Guides and standards can be of assistance as well as equipment manuals. Step back, and those standards I showed you, for example, are great references. They don't cost anything, and they help you in that process. Step back and look at the whole system. Focus on the point of failure will cause you to miss other drivers or opportunities. Prove every assumption. And I've got a case study related to this. I believe I have it in here. If I don't, I'll return to it. And it had a direct impact on the U.S. military. And it was something incidental. And I said, I wonder if, and just put it at the end of the thing. Didn't expect anything to come out of it. We got the information. It turned out to be the root cause. So it turned out to lead to the root cause. So prove every assumption, document it. If you can't, leave it blank until you can. You can have open questions at the end of an RCFA. Stay away from assumptions. Human roots, error and training. Latent roots, meaning something occurred that caused prior damage or conditions that are waiting for a trigger. I've had a number of those, including one that caused the gas prices in the Midwest to skyrocket one year. Physical roots, damage or other effects. The concept that something just wore out is rare. Too much focus on the bathtub and wear out curves, which are rare. Bathtub curve. It's a human being. For some reason, everybody keeps using this as the actual, we relate people to machinery. The bathtub curve is extremely rare. I'm an industrial engineer. I used to teach this stuff in college, and it just grates at my nerves when I see people writing entire articles on the bathtub curve, which is an actuary curve, meaning it was used, which was used by insurance companies as early as the 1500s for human life. And it's supposed to be, that's why we call it infant mortality. This part in the middle where it's average, and then the end wearing out, it's old age. The average thing in the middle is parts break, or you get run over, or whatever else. That's a human being. That's not a piece of equipment. Very, very rare. More likely, you're going to have one of these. This bottom one, that's electronic. That's your electronics. That is what they try to say this is. So in electronics, that's pretty common. It's one of the more common ones. For random, meaning the same reliability the entire time, that's the next most common, and something that starts out with high resistance of failure and increases in potential for failure, or I mean, low rate of failure and then goes to higher rate of failure. That's rare, but there. Okay, so all of these are age related. No, I mean, if I look at a tire, maybe I could get this. Your car tire, it's going to wear out over time. However, my last set, I just had a piece of truck go through the side of the tire, but that's besides the point. That was a simple root cause. So what is a proactive approach? Preserve the data, order this analysis team, analyze the data, communicate the findings, and track the results. Always, always, always. This should be a Sasquatch now, but that's coming. That's the next version. Always, always, always support everything you do with evidence, evidence that's as irrefutable as possible. Stay away from the sketchy stuff. So we start looking at these. We can start at the top. So this is a starch motor failure for a facility. And let's say, is it a winding failure? Ground fault? Nope, wasn't true. And so behind this, I'll have, what the details were, what we did to test it, and then the results. Turn-to-turn fault? No. Coil-to-coil short? Yes. Phase-to-phase fault? No. Winding contamination? No evidence of it. Whoop. So then I come down here to coil short. Were there harmonics in the system? No. Was there ground mode noise? Yes, there was. Was it a soft start issue? Because there was a soft start involved. Yes. Was the ground set up properly? Soft start setting. So this is one that's in process. So we knew that there turned out to be ground mode noise. So yes, and that was associated with these. If I go back here, output from the soft start stop settings. So then we come over, and the next one is bearing failure. Were there environmental issues? Okay, latent root. Okay, the temperature in the area would exceed 40 degrees C, which is the ambient temperature of the machine. So bearing failure could definitely be caused by ambient issues. Matter of fact, we went up there in August and it was 110 degrees Fahrenheit. For those that comes out to be about 41, 42 degrees C. And it could get warmer than that. It was not a dusty environment, it was relatively clean. Mechanical defects, such as motor misalignment, nope, didn't see any evidence of that. Then we continue. Electrically driven defect, there's ground mode noise again. So I've had it in two places. You can have that occur. There's technically a dotted line between them. And electrical fluting, which also did occur, which is then a latent root. So where you see where I have it labeled, latent root. So that's contaminants and lubricant, but that actually turned out to be related to the electrical fluting. Okay, so then we were able to go back and take a look at it. This is the winding failure that occurred in that particular machine. Now these are up on a high floor in a building in a corn miller. So we were doing investigations and taking a look at it. So evidence, yeah, this failed. As a matter of fact, it's a coil-to-coil short, and it looks suspiciously like something we'd see on a VFD. We also saw, in addition to discharges, even though it's on a soft start, we did see some other discharges occurring and evidence of discharge, including the fact that cage was no longer allowing the balls to spin properly in the housing. And part of that had to do with stuff with the cage and the grease itself because of the discharge. And you can see the darker color here from the heating. So other things we did included testing. We did our own experiments. We tested the controls. This is a soft start to see what's going on. And this is the incoming side of the soft start. And these are the leads are going up about 300 feet. We did test the ESA stuff, and it looks relatively clean. There are some things in here, in particular in voltage, are a little nasty, but you know, not too bad. They're relatively low. This is more data. This is the torque. This is the operation of the machine. Starting up, a little bit of oscillation that had to do with the fact that they were starch pumps. Now, when we tested on ground during startup, this is the voltage, or this is the current. Okay, so we had on ground, this one here is a peak current at 130 amps. Fast rise time, by the way. These are very, very fast rise time peaks. So we grabbed that, and then we also looked at what happened once it all settled out. So this is also on ground. And then we also found some of the amps, some of the current came out to be about 6 amps peak during normal operation at no load, and up to 16 amps under load. So we went back and we discovered that the ground leads that went back to the soft starts were in the conduit with the output from the soft start. The motor was also connected to the building ground, and the whole system was on a high resistance grounding system in which the fuses had blown. So it was a floating ground. So we had a ground loop issue. And a couple other things going on during startup. So, and the cable, it wasn't a cable, it was loose conductors in conduit, which included a ground for a machine, 300 horsepower machine. So we ended up with this stuff here. Well, the insulation system doesn't care. Now I took also measurements, I think. Yep, here we go. Discharge measurements on the motor. That's I got a little bit of gray, so that was probably about 2019-ish. So I'm taking measurements on the shaft ground here, and then we were also taking measurements from the machine to the building, and then we're also taking ESA measurements or current signature measurements on the ground cables, all part of it, all part of the study to figure out what was going on so we could come back with a solution. The solution was to either put in proper cables in the conduit or take the ground out of the conduit. And then we had to come up with some other stuff, which included a coiled filter on the ground going to the building in order to smooth out some of these current spikes that we were seeing. The actual surface of this machine, I wasn't too concerned about leaning on it. You will notice that whenever I'm doing anything around something that I suspect is a electrical hazard, you notice I'm not leaning my other hand on there, and it's actually in my pocket so I can keep it away. But we'd already checked the voltage was not an issue there, and the grounding was good. So review, winding voltage reference to ground. Insulation cannot determine where the fast rise impulses were located. So basically those fast rise time impulses were treating the insulation system just like it was on a VFD, even though it wasn't. The noise is introduced when the motor is energized. It ended up with a ground loop with unshielded cabling, winding seeing the same type of issues as if it was on an inverter. Noise coming from the ground grid introduced when the ground loop is closed, and then it's also a high resistance system. So soft start undersize for the application was also part of it. And I will note the manufacturer was involved in all of this. And part of what we discovered was that one of the guys involved in the project was working on an IEEE paper and wanted the data. That meant he was allowing these things to fail and not looking for a solution so he could write a paper. So what are the ground current limits? There is no standard. That was a bit of a surprise. There is literally no standard behind there is no standard behind the limit. So we basically said, based upon literature for manufacturers, said the kVA divided by 1,000 is the amp limit. that means it's generally going to be in the milliamp area. So this 158 milliamps or 0.158 amps. I have not seen stuff that low. It's very rare. We'll just put it that way. Normally I'm measuring ground systems in amps and not low amps. Startup, we hit spikes up to 135 amps peak on ground. And then we also just basically a fluke multimeter. By the way, we also discovered that that fast rise time stuff using the fluke instruments or any type of RMS or true RMS instrument is not going to detect those properly. Severe winding fault due to lack of protective devices. So we came back and said a ground shunt. That meant a coil around the ground, a shaft brush to protect the bearings, and they came up with one that mounts through the fan cover and can be carefully corrected with shielded cable, okay, or removing the ground from the conduit, preferably the shielded cable. So after we implemented it, came back, took a look. Yep, still had relatively high grounds, but smoother waveform on the ground. It reflected it because they did not correct the ground wire. They did not correct the cable. And the common mode noise was pretty much gone because we filtered it out. This ended up in a research study that ended up with the relative harm index. So let's get into insulation systems, and then I think I have it set up for a short break right after that. For me, it'll be just to stand up and sit down. I might just continue through it if nobody minds. So any questions on those steps so far? We're going to get into how to evaluate components in a machine. Nope. Okay, so just so you're aware, that's an 8,000 horsepower, 13,200 volt compressor, synchronous compressor motor. The repair shop that we did, that we assisted in doing that repair, they were going to do it vertically. A lot of places do. Another guy from GE and I convinced them to turn it on its side and treat it like a hydro. Made the winding go very, very quick and very, very accurate. Reduced a lot of the problems we have when people roll the stator, and made it easier on the technicians. Oh, it's raining. So when we get into root cause failure analysis, we do a full, I literally refer to it as a forensic. So chaos engineer who does forensic analysis on things that blow up. So when we do the initial assessment, why does it appear the machine has an issue? Is it a full failure? Was it electrical testing that identified it, or was it visual? Who was involved in the assessment? And then you need to start looking at gathering those decision makers and experts. Now, doesn't mean you have to have them all in the same room at the same time. I've had to do some where, you know, the purists say don't do this, but I've had good luck doing it where I've gone into a facility and you know, I know where the experts are. We'll start the thing, and then I will go to the experts one at a time and gather the data needed, and then start working on the chart and share that information as we continue on so that they're able to do their work. This makes it a lot quicker, a lot faster. The main thing is getting that evidence and then verifying that your conclusions are correct. Okay. What is the location of the machine? Is it easy to reach? Is it simple to tear down? When does a machine need to return to service? Is it urgent? Is it an emergency? Is a sister machine failing? You know, basically start asking questions around it. One of the things you have to remember is you will run into a lot of corporate resistance, meaning C-level and management level resistance if you're trying to push this stuff through. And you know, they need to get this thing back up and running. It's urgent. We need it up now. You know, we don't have time for this. Well, you need to make sure that you can gather that evidence and work on things and get that evidence separately, whatever you need to do to get it done and to meet the demands of the customer. Okay. You where is a suspected issue? How does the machine look? Basically preserve everything you possibly can. So what are some of the factors influencing our expectations for repair? So this is a 13.8 4500 13.2 kV 4500 horsepower compressor motor. It is deemed life critical. There are a total of 6 of these and 6 lower horsepower machines. They can only lose 2. We had problems with all of them. So this is the repair shop. So we need to be there during the teardown in order to identify anything that's unusual. I just won a court case on behalf of Phillips 66 by just doing this. We had a pipeline issue where all the manufactured motors had the leads coming in, 41 60-volt motors run off VFDs. Once the leads had penetrated into the motor and the bearings were lubricated with turbine oil and the breathers and everything, all the rubber inside the machine was actually rubber. It wasn't insulation material. It was a knockoff, basically, of actual insulated cable. We discovered when we did the RCFA. Now, I'd been standing next to that thing when it was started twice, and when we had looked at it, all of the material, all of the rubber it was gone. So we had conductors within a half an inch of each other carrying 4160. Luckily, they did not start across the line or it would have been catastrophic. Pumping natural gas. And they were not explosion-proof machines. So if one of them had failed, it could have caused a catastrophic explosion, and if there were any personnel there, loss of life. So the pump I went and worked with the OEM on the motors, got it resolved. They had as soon as they discovered what was going on from the RCFA, there was no argument. They were paying for brand new stators to go on. The pump company, but it had to go through the pump company. Pump company received the money to do all that, and then decided that the customer was overreacting by pulling all the motors and replacing that. They should have waited till they failed, was literally their opinion. So in the court case because during a period of time, 2020 occurred, all of the data was destroyed or damaged at the original lawyers and at the facility, and the people who left, well, their computers were wiped out by their IT department. So all of the evidence they thought was gone. So they contacted me and they wanted me to do, to write something up saying what we observed. Well, I did the RCFA. I had everything on a backup drive, every bit of evidence. So we produced all the evidence, gave it over to the other side. And then the day before the day I was heading to the airport to get on a plane to fly for the federal case, basically because they decided not to depose me, but they read through my stuff and they said, why is the expert so pissed off? And the response was because he was standing next to the machine when it was started twice and knew the potential for whatever, because in my report I said, their expert suggests that the funds should only be released upon the reliability trigger, which is explosion and death. So I'm known for some fun stuff. So anyways, observing these being torn down can identify things, because when we went in, I had gone to do that investigation with motion amplification because they were having a problem with movement of the pump and motor. And we found a foundation issue, but when we were taking down the motor, because part of the problem they had was something called mud flies, it was all in Texas, blocking all the ventilation. So they did have their own maintenance issues. When we took off the hood, that's when we identified this additional thing that was a latent issue that was not part of the original problem. So when we start getting into tearing them down, this is the dissection. This was my 24 megawatt cogen unit at National Institutes of Health, in which we were doing an investigation there too. You know, these can be quite exciting. This one here is from a repair shop. It might be difficult to see on your screen. It's a little difficult on mine, but there's a little wedge taken out here. Situational awareness. We would have gone there because a motor had been pulled out for general overhaul and it failed a high pot. And so when I went, we set up the high pot, cranked it up, saw the flash, which led me right to an air vent in which I pulled out a microscope that allowed me to see depth. So this is a picture from that microscope. So I zoomed in and I saw where the failure had occurred. And I go, that's interesting. That's a mechanical failure. And I went to put down my stuff, and sitting on the table on the desk, because they had said there was a failure and that they would just send me the records. And I go, no, I need to see it. This is an expensive repair for taxpayers. So I go out there, and sitting on the winder's table was a screwdriver with a little bit of this insulation still on the tip. So they had physically damaged the winding. So that made it into a report. So it gave the utility involved decided to pay about half of the rewind, but it did get rewound because of this. The motor shop in effect didn't make any money on it. They barely got any materials covered. So the degree of visual damage, electrical testing results, indicators of where to look, age of machine and service hours, conditions and location of the machine, clean, dirty, moisture, chemicals. So like in a case like this, what did we do? Well, let's find out where it's located. Well, how do we do that? Get the AC high pot tester, crank it up until you see a flash or you see smoke or you see whatever. There has to be a way of identifying where the issue is. Procedure, visual assessment of the machine, tear down the machine, visual assessment of the rotor, visual assessment of the stator, basically go through everything. Removal of stator coils and bars from the machine. This is critical. Number one way that everybody removes the coils in a motor repair shop, toss in a burnout oven. You have destroyed all your evidence. Dissection, this is a big one. We're actually working on a standard right now in IEEE for how to dissect coils. The big argument right now is between people like me who do this for a living in order to identify failures. I've got a bunch of railroad-based machines going to a local repair shop in which I'm going to be there and we're going to oversee the tear down of the coils to determine why they failed. My intern gets to see it too. So he, new guy. So one more year of school and he's going to have some experience. The other guys are having. But anyways, the argument we're having right now is the OEM says, oh, no, all dissection should be done by the OEM. And I'm like, no, if I'm involved in a case that involves your company, I need to be using the same standard you are, so that we are showing apples to apples, between however the arbitration is occurring. So it could be removal of individual layers versus cross section. So this is cross section. This is removal of layers. This is the wind turbine cable, by the way, and this is the black stuff on there is a dielectric material. Looking for physical damage, looking for any foreign bodies in there, evidence of burning or charring. Quality homogeneity, basically, is it all one piece or general condition? This is from that same one, and you'll notice this. This is all on the outside, on the outer edge of the conductors. So here's a little secret. For those who ducked off early, they're only going to see this if they watch the video later. So if I have a failure in a winding and it's a cavern, meaning that I have an opening towards the outside and all this area in the middle is open, well, that's because a winding short occurs as plasma, which is a perfect void, perfect circle, okay, a perfect globe. Well, the physical properties of the material are going to make it not a physical globe. Okay, so, but if I look at it and I figure the geometry, I can figure out the center of that geometry, and that's where the failure occurred. Okay, now if I have a cup, like this case, this is outwards, then that means it happened up on the surface. So this was a ground fault that failed here and then kind of damaged everything else. Okay, so it failed on the edge, top edge, that would be the top, by the way, top edge of the coil. These are the individual conductors. I'd removed the material off of it. So once a coil or bar is removed from the stator, use a knife to gently remove the layers. We also, some slides back, I showed you that. Here, let's go back to that. This is one of the layers. This is with the microscope. Now I use these cheap little Celestron microscopes, and I forgot to take it out, probably in my backpack. Okay, so follow the path. Failed bar may show burning. Follow it. It will lead you to the actual issue where it failed. Take notes and lots of pictures. I mean, nowadays, you don't have an excuse. Nowadays, I have this thing, and I've got a couple of years worth of gigabytes of photos. I think on my backup drive, I have something in the effect of about 2 or 3 terabytes of photos going back decades. I keep it all. Makes a great thing for presentations too. You know, how many of those come apart easily? So if I take a razor blade and I peel back, or a knife and I peel back, and they peel back easily, it may not have been properly cured. If I peel back and it's really hard, it might have been over cured or aged, you know, things like that. So some of that is experience from my being a winder. Okay, so take photos. Consolidated insulation cannot readily be taken apart, so finished insulation. Alternative is a clamshell dissection. I'll show a picture of that. That means that, yeah, so I've on the conductor, so that was the conductor for this other one. So we cut across the top and then we just open it up like a clamshell. It also then allowed me to peel back the insulation, but there's where the ground fault occurred. Okay, cross-section techniques. You can see how rough cut that is, right? Okay, so like I said, there's a standard now in process. It will not be out until either next year or the year after. Once we're finished with it, it takes 6 months. We just had the meeting on it in South Padre Island a couple of weeks back, last month basically, and it made some progress. We're doing, you know, whenever you hear, oh, Howard's on another teleconference, well, I'm usually on a standards meeting. It's not always a customer meeting. We're doing also IEEE standard 1 right now. We just finished all the comments going out for reballot right now. And in that, that's insulation grades and stuff like that. So bandsaw, hand saw, diamond saw, wet saw. Okay, as I go through, bandsaw ends up looking like this. That's a bandsaw. Handsaw, don't do it. Diamond or wet saw are better. Wet saw, I've done a few, and I had a court case once, and somebody went in there with a wet saw and just absolutely destroyed the evidence we needed, which was a big issue. I won the case, and it's the famous pink flower and dental floss defense, but I'll leave you hanging on that one. Creation of artifacts, meaning, am I going to, when I'm doing this, delaminate the material or, you know, cause smears? It takes a trained eye to look at this stuff, right? Pot and polish, basically polish the end off so it's nice and smooth, and make sure that if there's copper between these, that it wasn't something that got smeared over. You know, if you push it through the bandsaw, then it'll smear. Microscopic assessment, like I said, let me see if I have it. You can get them on Amazon now, and we're talking about at most $100 investment. No, sorry, folks. I must have put it away. It'll be in my toolkit. So remember the goal for the assessment. We can all get caught up in the science of the moment. So remember that, and that was one of the lessons that I took to the standards group meeting is, hey, folks, it doesn't have to be that advanced. Now, I've been to some of the OEM sites, such as GE and stuff like that. Their tools for doing dissection are unbelievable. I mean, there's no way a small company like a repair shop could afford even their cutting saws for doing a dissection. But how do we make it equivalent, or something where, you know, both sides can communicate? Don't worry about too much detail. That's one of the things about reliability engineering. It's like, I can solve something, you know, does it really need that much? Here's a dissection of a high voltage coil. This is at the knuckle or at the turn. You can see all that material built up there. These are not defects. Those are literally holes in the winding. So this one would be probably for a large generator, and that would be for cooling water or hydrogen, depending on the type of machine. So you want to look and make sure that this is cut across right, and then you want to make sure, you know, things like if you hit a spot where this happens to be collapsed or something, and you know you found something, and then you look at the materials. And this is obviously probably a hot press or B stage winding, just the way it looks, and not a VPI. So, and you can see a slight step in between and stuff like that. But that dissection, that's not, yeah. So here we go. There's my dimensions there. I want to get dimensions too, because how did it fit in the slot? Assessment of insulation. Overall, consolidation, general quality, and that it's homogeneous. Mica. Mica is an actual insulator versus a dielectric. Is there sufficient insulation? Is there evidence of partial discharge, which would be, you know, etching or damage? Delamination, wrinkle and tape layers, number of layers, uniformity of layers. I had a situation where I was going in to investigate multiple failures of a 2300 volt, or I'm sorry, 4160 volt motor from a power plant. Got it back into that repair shop, and you know, went ahead, removed the coils and did a cut, and discovered that the VPI material in the slots only penetrated about half the way through the material. Well, they had seven half laps, which comes out to 14 layers of insulation, and then their VPI varnish hadn't been checked for viscosity. When we checked the viscosity was so far out of spec, there's no way it would have penetrated. So, you know, that meant that they were basically putting dry windings into an actual application, and it would last several weeks. So yeah, it was a warranty as a result, and the root, you know, then we go back, and one of the causes, not the root cause, was that the viscosity was high, and we went back further, and that was the one time I was able to point at a person. I'll just say that. So copper stack alignment, type of insulation for medium voltage, copper corners, etc. There are tests that can be done as well, including void identification of voids, and then also types of materials. So here's one, and you can see when I get in there with the microscope, okay, insulation layers are clearly seen. You can actually count them, just like, you know, if I chop a tree or saw a tree, I can count the rings. Known to be from saw cut, so some tearing at the surface out here. Note that the insulation is still well bonded to the copper. So that's the other thing we're looking for, is delamination. So you can literally just see the edge, and this is smeared copper here and here, but along the edge you can see that there's a layer that's very, very thin that happens to be the enamel. So that is actually in pretty good shape. This is delam. So this is where it's delaminated or pulled away. And that's where partial discharge can occur, especially in systems over 6,000 volts or low voltage systems that are on inverters, such as wind turbines. Close-up of good insulation. There's my copper. This is resin, and there's the mica layers. This, on the other hand, is when I run into wrinkles, meaning that the tape wasn't applied exactly right. So I have wrinkles. Those are all, believe it or not, those are electrical stress areas. So that could lead to a failure. It's also evidence of improper, poor workmanship. And then you also want to look to see if there's any contaminants caught up in there. This is dry mica here, meaning it's slightly different color, meaning it didn't get properly penetrated. Okay, so here's more wrinkles with resin in it. And those end up with lumps of resin or possibly voids. And the voids are what you want to avoid. Avoid the voids, not avoid the noids, avoid the voids. Tape tension, things that can cause some of this: tape tension, tape stiffness, tape thickness, and how long they take to process everything. Okay, so conclusions for this part. And this is one of those ones I said, a clamshell. Remember the goal for the assessment. This is not trivial, meaning this is the time, if you're the engineer doing the investigation, this is the time that you want to be on top of the sorry, need to do that. This is the time when you need to be present. Don't wait for a report to come back saying, oh, this is, da da da. No. Whenever I have an RCFA, I've had people say, well, can we just send you the pictures? Absolutely, but that's not an RCFA. I'm going to give you my expert opinion based upon what you send me. So if I'm going to be part of an RCFA, I am going to be on site during critical operations where I need to see this stuff. That is absolutely important. Remember the goal assessment, it's not trivial. Use experts, meaning use people that understand what you're looking at. Take a lot of notes. How you dissect can cause artifacts. Good insulation is hard to take apart. Burning and charring are places to look. Sometimes you cannot see it visually. Dielectric breakdown may have destroyed the evidence and use all the information in hand, basically all the history. Okay, so give everybody a second to breathe. Wow, either I've got everybody sleeping in front of their computers or there's some interest. Okay, good. Okay, so I'm not going to take the coffee break. This is the actual material that we gave at the conference. So here we go. Let's start talking about the tools, the test, how to do this stuff. By the way, this is my don't ever aim one of these motion amplifications at the base of a wind turbine presentations. Overview, we're going to talk about offline testing, low voltage motor circuit analysis, and high voltage motor circuit analysis. Online testing, okay, analyzing a machine and machine system forensics, critical thinking. So let's get started. And remember, whenever you're doing testing, some of the stuff can get pretty dangerous. Always remember, if I'm investigating the motor or generator, it's part of a system. There are things outside that can contribute to my problems. So I need that data often as well. So let's talk about high voltage and low voltage. So that's an all test 5 at the time. This is an Electron 12 kV high output surge tester with PD and low voltage testing. I just did an article on this on reliamag.com, the reliable magazine, last weekend. So it just came out earlier this week. If you want to know more about low voltage testing, I'm not going to get into details on it because that would turn it into a bit of a sales pitch because they're the only ones that do that particular type of testing. Although They're now doing sweep frequency, which is supposed to be an emulation of that. So anyways, when we get into ohm testing, I normally say you do phase to phase. There's some discussion right now of phase to ground, and also the resistances across grounded components. So I'm going to just say for phase to phase testing, you do phase to phase. Remember the device that you're using. So standard tolerance, if I'm picking up an AEMC or Fluke multimeter, my tolerance is going to be about 0.2 ohms, which means I can look at the winding of a motor at about, up to 10 horsepower. Above that, I'm going to be lower. So I need to have a micro or a milli or micrometer, or, so 0.001 ohm or 0.0001 ohm or better. This is a 4-wire Kelvin, and this would be a 2-wire milliometer. I will need to, when possible, correct for temperature, especially if I have a spec sheet for the motor. So it'll say, usually if they're following CSA 390, IEEE 112, or the equivalent IEC efficiency standards, they will have the phase-to-phase resistance there, or even the circuit resistance for different parts of the winding circuit, depending on the machine and the manufacturer. And they'll say at 25 degrees C or at 20 degrees C. So you want to adjust the temperature to that. So normally when I'm doing this type of test, I want to make sure that the machine is at local room temperature, or I'm taking temperature on the machine. So resistant, and then I also want to make sure I use the appropriate thing for whether it's copper or aluminum. You will see as I go through this, I'm going to refer to everything in degrees centigrade, just because now everything we're doing in standards is transitioning away from Old English to SI, which is basically metric. Current testing around each phase. Now, I don't know why, but I keep running into people that do like CBA or BCA or some weird combination. In the military, I was taught ABC, 1 to 2, 1 to 3, 2 to 3. So that's the way I present it. I like being repeatable that way, because if there's a question on something, I know where to go. If I'm doing any type of weird random whatever, I don't know where to go. So as I walk through, it could be A, B, and C. So if I get an unbalance in current, whatever that unbalance is, there's some things I can do. Let's go back to that. I'll cover those. I'll cover that. So now in a 3-phase machine, if I swap any 2 of those leads, I'm going to reverse the direction of the motor. However, if I take A and put it on B, and B put it on C, and C put it on A, I've rotated the phases. Now, if I measure across it, if it's a small motor and it's a concentric wound or basket wound machine, I might suddenly find that I have balanced current. Don't panic. That means you've got an unbalance up the line somewhere. But if I have a phase impedance issue or something wrong upstream, what'll happen is the unbalance will remain in that phase. So if I have a high B phase, it'll stay as a high B phase. Now, if it rotates, even though the numbers will be different, as I rotate the phases, if they follow so that this high phase B now becomes high phase C, then I know it's on the motor side of things, and that's what I need to investigate. Insulation to ground. Wow, this is, it used to be prior to 2013, so the old IEEE 43 standard. There is an IEC standard in process right now, because Europeans got tired of having to listen to us Americans tell them how to, just kidding. All of these groups have international bodies. We try to homogenize everything so that they're similar. But so IEEE 43 is kind of the global standard still. So it used to be that you had to tie all your leads together and then that to ground. Now it doesn't define that, including the latest version we're working on. So here's what you have to remember. Regardless of how I do it, I got to do it that way each time. And it looks like I'm hanging up a little bit again. Give this a set. Oh, probably because of the animation. I'll get past this real quick. So when I go from, say, any one phase to ground, if I'm going to do any trending, I need to do that consistently. If I tie them all together to ground, I'm going to get a different result from that. Okay, there we go. That's what it was, the animation. My system is not liking animations. Leakage current, no, but yes, at the same time. Something similar to that. But what we're looking for is a certain amount of current with a DC voltage applied. So a lot of the testing we do in insulation systems are variations in looking at the capacitance of that insulation system. So when we look at a standard insulation resistance test, corrected temperatures, and we correct temperatures to 40 degrees when we do these tests, is this a pass-fail for the machine? If I read 5 megohms or less on a random on stator, is it bad? No, not necessarily. Matter of fact, in the military, Coast Guard and Navy, we allowed up to 1 megohm, and then that was our decision point of whether it was good or bad. Now, why do we do that? Well, it could be contamination, could be humidity, could be all kinds of things. No, what these actually stand for is the minimum reading to do higher voltage testing. That's it. That's literally in the standard. Now, correcting to 40 degrees C, that's become a bit of a challenge because, for some reason, people who wrote the modified standard in 2013 really pushed that, and I was on that group, by the way, really pushed that, because of all the new materials, that once you hit 40 degrees C and you got hotter than that somehow you had to do these wild calculations. So about half the standard now is how to calculate for this type of material or that type of material, et cetera, et cetera, et cetera. I'm going to tell you, don't bother. We will correct temperatures to 40 degrees C, but no reason not to do the old way and remain consistent. The big one is the temperature, or is the voltage selection. Now, here's what's important, because I keep hearing, oh my gosh, if I do this voltage, I'm going to damage the insulation. An insulation resistance tester, or Megger test, sometimes called. Megger is a brand name. It's kind of like saying Kleenex for facial tissue. But in any case, battery powered in particular meters cannot put out enough energy to damage your insulation. Otherwise, the machine would have failed already. Okay, so you've got these. Now, altitude will have an effect. So when you get above 3,000 feet, 3,000 feet, you can have some significant variations. Other things is air pressure or even the surrounding air. So if I'm in a highly polluted area, don't see that as much these days, but if I'm in a highly polluted area, I can get variations in readings. And we did a study in 2019, so I think I actually published it in 2020, in which we took it would have been 2019. We took the air pressure and brought it down to 0.08 millimeters of mercury, which is, or inches of mercury, whatever it was. It was almost pure vacuum. Almost pure vacuum. And of course, when I have still some material there, that means my insulation resistance dropped significantly. So air pressure most definitely has an impact. So things to consider. But voltage, on the other hand, even if I've got a 480 volt motor and I go in there and I use 2500 volts, the only thing it's going to read is my reading will read lower. So the purpose here is to make sure that I have a voltage that's consistent when I test between. The other thing to remember is using two different instruments, I can get two different answers. Adjusting for temperature, you adjust off of 40 degrees C. So at 40 degrees C, this will be about 1. And then if I go up 20 degrees C, you can see that I am 2. And yeah, so basically it should be about double. I'm sorry, it's for every 10 degrees C, I'm going to double the insulation class this way. And for every 10 degrees C cooler, I'm going to reduce the insulation class by some value. So there's a definite chart. Use that for every 10 degrees centigrade, double or reduce off of the 40 degrees C. Okay, so now we get into a couple more. Now these are, right now, we are having fun with these as we're going through IEEE 43 again. I'm going to stick with what's published for the moment, because there's an argument starting again between the OEMs and the end users, because we've got more end users again finally in the standards meetings and testing companies and testing engineers. So ratio of 1 minute to 30-second insulation resistance testing. You notice only accurate insulation systems less than 5,000 megohms. So that means if I end up with a value that's say 1.2 and I'm at 6 gigohms or 6,000 megohms, then that's a value that I can trend, because this is not supposed to be temperature dependent, but you know, I can't use that to say it's questionable. Now, if it drops below 1, then you're questionable. It should never decrease. It should always be increasing or staying steady. Okay, so that's that. Polarization index, if I do the direct numerical PI, again, it's the same thing, except I'm going across 10 minutes. Technically, if I go to one of the annexes or one of the sections in the back of IEEE 43, it'll tell you how to calculate the length of time to apply it. In the body of the text, though, we make it standard so that if I have two different groups go in to do PI, they are both getting the same results, okay? So it's a ratio of the 10-minute to 1-minute test. Let's get into something called the insulation resistance profile. We finally got it added to IEEE 43 in 2013 as Annex D. It went from the 10 pages of annex that Dave McKinnon and I wrote to one paragraph just saying it can be done. It's now about half of the standard going into P97, or it'll be IEEE 97 when it's released. There is an old IEEE 97. If you go look it up, it is a completely different standard. The number, that one was retired. The new one coming out will be for DC testing. And it actually, we're going through this right now, but we're trying to have results included in the standard, because it's how to do pattern recognition, and the patterns follow certain things. Okay, so been around a long time. As a matter of fact, I have a book somewhere. I've got it out of sunlight, but it's in my office here somewhere, from 1913, written by a Charles Penrose. That's how I got it. Somebody gifted it to me from a repair shop, from a Charles Penrose, that describes this test. I was taught to do it in the Navy, and then when we presented it at IEEE, everybody, we'd never heard of it before. So it has been around a long time. It's included in certain technologies. This is an amprobe, high voltage insulation resistance meter that'll do these. PDMA has them. You can see I've got almost no gray, so that would have been 2016. Review of 690 volts, 4160. Okay, so we're going to take a look at those discussion machines. So if I come in here, now I know that's 2010 because I remember doing this one. This is a 1 megawatt hydro generator in upstate Michigan. We're doing this in August, so everything's kind of damp. So we ended up doing here was we cleaned this up manually. This instrument takes a test result every 3 seconds and maps it. So I don't have what I'll talk about later is discharges, but we included these in the standard because somebody suggested 5 seconds. And no, it didn't work. I mean, we would miss a lot more. So every 3 seconds was the decision. And you notice I go out to basically 121 seconds here. But this first curve here on this rotor, this one here is when it was dirty and kind of damp. And then after we cleaned it and then we put an air dry varnish on there, this is before that, we ended up with the curve being higher after everything cured. So this gave us a quality control measure to make sure that what we did worked. IAC did not release measurement of insulation resistance. Is that it? I don't know. We were just talking about it recently. It might be there. I know they're working on it again. The 60034-27-4 from 2018. Yeah, that might have been the one. IEEE 97 is that section for the PDCA is, and I'm not calling people out by name, so, but I am answering some questions that I'm receiving. That question on the PDCA, it's actually going to be Hydro-Quebec that's who's writing that section. Several engineers from there with a lot of input, including by Qualitrol. So Greg Stone is still involved in some of that as well. Although he's our PD expert, he wasn't able to make it to the last meeting, but because of world events and the ability for people to travel back and forth to the States or perceived, I don't know what's going on basically. But in any case, I'm just going to leave it at that. We were missing about half of the usual attendees for the standards meeting, so we had them all online. So Greg was there. We were talking about this. Don't know which parameters for those we will be using. They're trying to make it generic. What they did do is send out a survey through ESA. That I collaborated with ESA to get that out to them and a bunch of others to see who did the PDCA. And yeah, nobody except on the utility side. So the insulation resistance profile, everybody goes, oh yeah, we do that, or insulation the polarization index test. So that yeah. So you're referring to the charging discharging thing. Okay. The other thing we can do when we do this, this one has, on one side I have 3-phase, on the other side I have the neutral. This is an old GE machine that came out of storage. When we put all the leads together, this is the amp probe, so it always shows 0 on the first one. It comes up and is fine. When we split the leads, we saw a difference. Now this here is just a transition in the instrument. That's not a discharge. But when we opened up the machine to see why one was separate from the other ones, visibly separate, not necessarily bad, just visible, we found a literal rat's nest. So the rat's nest here and up underneath, that one, we found little mouse skeletons and everything else in there. They had also started mouse urea does not do great for insulation systems. Neither does the fact that they like to eat it. So there was a lot of damage to the insulation. We were able to luckily clean it up and do an over dip in order to salvage it. It was all surface damage. This one here is a wind turbine generator. Yeah, pardon the colors there. This was a we had at the repair shop I was running, we had a contest between two wind sites. We had a former, we'll just say graffiti artist as the painter at this company. Is still there, and he got all excited because it was like, hey, can you do this with the painting on this one? Because the first motor we sent back had racing stripes on it with flames and a skull, and of course it blew up. But that's neither here nor there. And then he would, they would call up his, yeah, the other site, that the generator that they sent up there, the guy hates Dale Earnhardt. Can you do a paint job showing his car? And poof, we did. And back and forth. The other side sent, an opposing football team and so on. We had a lot of fun for a while. So in any case, doing one on this one, this would be a final test with everything attached. That gave us in gig ohms, that gave us a record to go off of. And this I can tell right off this one, this is with that little amp probe I had. So no discharges going on. And so I'll come back onto this, I think, at some point. But when I'm looking at an insulation system, there are times when I'll have a sudden charge up and then discharge down. And somebody was trying to tell me that's not possible, but we see it all the time. So there'll be a sudden increase and then it'll shoot down. That's capacitive charging and discharging. They'll hit a point and then it'll do that. And sometimes the insulation might start to degrade at the same time. Now, if it happens across the entire thing, that's usually contamination or wet insulation system. If it happens further out on the curve, that's usually dry and brittle. Early on, it's uncured and stuff like that. So we're including some of those waveforms as examples, including the rotors, including edge-wound rotors. And that is a big push right now from the Army Corps of Engineers on hydro generators. No, no PI value of greater than 2. Megger can, the instrument manufacturer can put whatever they want. A lot of their, I just picked up a portable Megger for a project because I wanted to have that for, there were reasons. It had certain features. And it still had the 1 megohm plus 1 megohm per kV in it. So yeah, a manufacturer can put whatever they want. If you want to follow standards, standards are always the minimum expectations of something. So and the PI ratio, that's part of the reason we're doing 97, because a lot of the new insulation materials will polarize too rapidly. Heck, on these two machines here, their PI is not to 1 minute to 30 seconds. It's 3 minutes to 1 minute. So that's the Electron, that's that 12 kV. This is the earlier version without the PD. Oh, I'm sorry, this one probably had, no, this is the earlier version without the PD. There's a result from this I'm going to show you, and it caused them, after I talked to the owner, to change the material of their leads. This one here is the Baker AWA. That is also their larger one. These are similar. This is a DX, or would be similar to the DX from Megger. Now it's Megger that owns Baker. The primary difference between these is the output. So this one puts out 60 pulses per second. This puts out 5. We ran into some stuff in the field as a direct result of that. For instance, with the 5, sometimes we'll miss some things. This one we won't. The other day I did a demonstration. We videoed it because I was showing my intern about some of the tests we do, and I brought it a stator, and I had a defect in the stator that would glow, you know, so we turned it on, we started it up, and I was just looking for the partial discharge of glow and have it trip. Nope, it blew right through that, and not only did it blow through that, we had multiple faults at different spots, and then it started running the next phase. So have to be very, very, very careful with these. Because when we talk about potential destructive, what it means is when I press a high voltage system across there, whether it's an AC high pot or a surge test. Another question. Yeah, okay, so question has to do with another aspect is a point that PI should be ignored if greater than 5 gig. I covered that. That's not changing in the new IEEE 43 at this point. Don't know where it's going to head. Our next meeting is in September. And I know you're an IEEE member. You can always, it'll be the materials subcommittee if you want to take a look at that. So it's part of PES, and I think you're part of PES as well, without mentioning your name. But yeah, so that's there. I don't think we're focusing on that at all. We're trying. I think the argument right now within that group has to do with doing machine rotors that are edge wound or even round and square wire, because the OEMs had convinced everybody that those should be not included in any type of insulation resistance, or I'm sorry, in any polarization index test. And insulation resistance value should be ignored. And all of us fought that. It got pushed through anyways. And now we have more backing with like the Army Corps and others. Some of the people with field experience are pushing back as well. So that'll probably be the major change at this point in time. It's not expected to be any massive changes because we're expected to make minor changes and pass that through. So there's a lot of things that are in the 2013 latest edition that'll be revised again and out probably, you know, when we start working on these, and I think we just kicked that off, it's 2 to 3 years out anyways. So different types so there's, even within the higher voltage testing, there's a little bit of difference. So this one here will do low voltage testing as well. The DX version of the mega units will do this 50 and 60 pulses per second output as well. This was done this way to reduce the chance of damaging something in the field. It's also very sensitive to certain things because of that reason. This was their answer to PDMA and all test. So a lot of repair shops use it. So this would be from an Electron because that's what I have in house. And hey, when you call on Christmas Eve because the rental place for your AWA sent to you instead an old oscilloscope surge tester with a Polaroid camera and wanted you to pay $75,000 deposit on it, and you call the company and expect to just leave a message and hope that somebody calls you after the holiday is over, the owner of Electron picked up the phone and sent me his loaner unit so I could do my testing on January 6th. So in any case, so I have an Electron. I ended up ordering one and he sent me that. So winding resistance, that's the low voltage test side. So usually what we do is you want to make sure there's continuity, and then most of these automated surge testers will do make sure there's continuity, insulation to ground test, just straight Megger test, a PI or DA, then a DC high pot, and if it's past all that, then it'll do a surge test. And some of them will do also what's called a PD surge, which follows an ISO standard. And then this would be the low voltage tests off that machine. So this will be capacitance, and then their dissipation factor, which is supposed to be an angle. The inductance between phases. Now this is slightly higher than 10 volts. So if you go to see that article I wrote in Reliable magazine, you will see the differences between these and what the impact is on sensitivity by using a higher voltage for a low voltage test. So, so in any case, it'd be in millihenries. That's just a measurement of inductance. That means a measurement of the coil's ability to hold a magnetic field. Then your impedance, which is the AC resistance of the circuit, a phase angle, that has to do with the condition of the insulation material. So it's phase angle related to the capacitance of the circuit, and then the quality factor or Q factor. So these you want to make sure that they're balanced, and it gives you a way to get an idea of what's going on with the winding without potentially damaging it. So if I have a machine that's running, but it does have a defect, if I do a high voltage test and I trip that defect, I have now made it so I can't run it. So I'll use the low voltage tests ahead of time. In cases, I carry an All Test 7 now. So I will use that and then I'll switch over to this after I made sure that everything's good before I hit it with a surge test, depending on what confidence level I want. Insulation resistance tests also measure the leakage. So you will always have in an insulation material, there will always be some level of leakage, meaning current flowing across that material. You don't get that in a true insulator. Insulation systems and electric machines tend to be a dielectric, with the exception of on low voltage machines, you'll start seeing this stuff called PEEK or PEEK that's coming out. It's a certain type of material that is a true insulator. It has certain capabilities, but it's also some bad capabilities. It requires careful handling, but basically makes the insulation system, even if a PD present for a low voltage machine from an inverter, eliminates any problems versus nano dielectrics, which can only be used on round wire right now and stuff like that. Okay, so megohm, and then a high pot would be the next one. You can see this is set up for a PI test, and it maxed out at these values. That's basically the graph. So it went to 50 gigohms right away and stayed there in that case. High pot means that in this case I did a 5-step high pot. So it's going to be stepping all the way up, and then it's going to measure leakage. Leakage is really high before anybody asks. I'll show you what that looked like. So it's doing good, and all of a sudden it has a knee right there. So remember this back here. This material right here, well, as it turns out, if you go across a knife edge in a connection box in a medium voltage machine, when you hit a certain point, the leads are also an insulation system. So I basically arced through the insulation system. So we ended up doing is I put a piece of cardboard under it. That's all I needed. Oh, I'm sorry. No, I took the glove off my insulated glove and I put that on there. That's right. On that edge. And then the surge with PD. Now this is the old one that they did it picocoulombs. Now they'll actually do millivolt PD values for them, and it'll also show up on the chart here. I think I don't know where I posted that one. I know I put the results of the test up on LinkedIn at some point. Okay, so let's get into electrical signature analysis for those who I think some of you guys, yeah, definitely some of you guys use it. I'll cover that really quick. That's Brian. He's a field service guy from, well, he was with Shermco at the time, and now he's with another repair shop, still doing the same thing. Spends 100% of his time running around with one of these guys, which is the empath system. So I took this picture because I was training him on doing wind turbines. So this is a wind turbine, the inside of a GE 1.6 Plus. and we're taking data off the cable and back, and then under, well, in the low voltage side, we were required to wear certain arc flash stuff, even though everything we're touching is class 0. Okay, so rotor bars, when I'm doing electrical signature analysis, this is rotor bars. This is off a 4,000 volt, I'm sorry, 4,000 horsepower, 4160 volt machine at National Institutes of Health. This would have been compressor 19. Very first machine I tested, we sent it down to a local repair shop. They removed a layer of material off here. It was basically a band that goes over top of these, so you can see it looks a little different color than the red. And you can see the fracture there, you can see a fracture there, and you can see there's multiple fractures. So this was because somebody somewhere along the way decided, do we get classic PRPD patterns with a surge PD? No. Surge PD is slightly different. Surge PD, you generally are going to use that in inverter applications. Sorry, folks, I'm bouncing back because I missed the question. I'm running back to it right now. Okay, let's see. I think 10 delta with transformer bushing a few times that happen in motors. D factor in that slide, something else. Yeah, we do run into that in motors. 10 delta tends not to be used that much in the electric machines that we're dealing with. It's not popular for doing a machine, primarily cables in the US right now, so I don't see a lot of them. But yeah, sometimes the, don't know why, actually, on an electric machine. And then do we get classic PRPD, partial discharge patterns with surge PD? They're slightly different. What you're doing is looking to see if PD exists at fast rise time impulses, just like in a VFD. So you're seeing if it's possible to end up with PD, and you want that any PD to show up above the voltage rating of the machine, just like doing an offline PD. But that again would be with a nice clean sine wave, right? So when you do the offline PD system and you have the power, the correct power supply, say you're in a 13.2, sorry if you're overseas, that means 11 kV basically, but a 13.2 machine. So you would end up doing, to hit 13.2, you would do an 8,000 volt per phase. And then I believe that generally, because I do it anyways, but I believe the instruction is then to go up to like, I think it's 8.6 kV as an over voltage to see if the PD occurs up even higher as well. That's supposed to be a very short-term quick test. But in any case, with the other one, because you got the fast rise time, you're just seeing if PD exists, and there will be a pattern there, but it's not going to resemble the same thing because I'm not putting out a sine wave, I'm putting out pulses. Okay, so let's cover electrical signature. So electrical signature is a combination of voltage and current signature. The original motor current signature analysis concept, and everybody called both electrical and current signature analysis in the 1980s motor current signature analysis. Matter of fact, the original patent from Howard Haynes from Oak Ridge National Labs, which was the first electrical signature analyzer, calls it motor current signature analysis. So right now we're looking at redefining the terms again. That's part of the scope of a project I'm doing with Seagray. So we finally have the terms fixed, because we have motor circuit analysis, which is MCA, which is an offline test, and you have electrical signature, current signature, and motor current signature analysis, which are the known terms. And then we have training companies running around now calling it MCA because they want to have their own little name, and it muddies everything when you're starting to try to talk and you've got training companies running around making stuff up because that's the term they want to use, so that, you know, whatever. Very frustrating. In any case, I'm going to pick up the speed a little bit, but when I take a look here and I see voltage and current signature, power signature analysis, basically electrical signature analyzer by definition uses a power quality meter type card. So you get power quality testing by default. Current signature analysis will look from, so electrical signature analysis looks both ways. Voltage is upstream, current is downstream. And for current signature analysis, you're primarily looking downstream. There's a few exceptions to that, generally in the wind industry. So for instance, we've got the first current signature analyzer out that successfully tests wind. The impact on that current from everything, including the driven load. By the way, this picture here was donated to me by Howard Haynes. That was from his 1989 paper. I've seen another company out there trying to claim all kinds of stuff, and they're referring to this as a 1995 paper. It doesn't have any 1995 papers. This one also came from that same presentation. When you're at Oak Ridge, you're able to do animations in 1989. But in any case, it was to demonstrate that every aspect of what's attached to the motor will have an impact on that motor current through the air gap of the machine. This also is from that paper in which he was suggesting, because of his research, which was on bearings and gears in motor operated valves, not rotors, as what a lot of people had stated in the past, including me at one point, because that was the misinformation I was given until I talked to him. Nope, he had identified all the stuff that I've been talking about, fans, belts, pumps, gearboxes, all kinds of driven equipment down the path. That's what it was originally designed for, not for testing the sensor. So the air gap of the machine is the sensor, and to say that it's only meant for the motor is like saying you use vibration analysis to test the accelerometer. So, so in any case, he saw it as a replacement for vibration in a lot of cases. Is it possible? Well, we've been doing it. So yeah. There are different conditions that you can pick up. This one I think still has the defect in it. So that should be 1 and 3 times. 1, 3, and 5 times actually. And this would be twice line frequency sidebands, etc. So CF means the calculation for where the peak is and then the sidebands around it. One of the things we do try to do with electrical signature analysis is the resolution, because we're seeing everything all at once. So to be able to sort out certain things, the data sets are usually longer in length. So the two technologies we use, one's about 48 seconds in length, so about 38 seconds for the higher resolution stuff. The other one's 120 seconds to get to 0.008 hertz. Rotor fault issues, sidebands. This also came from the Oak Ridge group. It was specific on certain things because people had asked about it. By the way, by 1995, he was using current signature analysis for doing fitness and athletics, believe it or not, and fighter jets. That's a combination. So let's take a look at a quick case study. This is a 4160 volt machine with a pump, again at National Institutes of Health. Here we have our insulation resistance test, which we did as a polarization index as well. You can see it maxed out here, and we have more or less a curve. We did the surge test, and this is another place where we had that spike. So we knew, and we went ahead and we did an offline test to just verify whether or not it was the leads or not. I had an assistant with me, and that person made the mistake. So then we did a surge test. Now there's line-to-line EAR and peak-to-peak EAR, which this basically looks at the repeatability of the peaks between each phase for line-to-line, and peak-to-peak is each impulse as the instrument sends out an impulse to make sure they're repeating. So it'll be a percentage difference between each pulse. It was funny because I had another surge person who, when we were at the standards meeting, thought I was, because in the past I used to have arguments with them for fun. He goes, "You're wrong." And I said, "Well, what is it?" He goes, "Peak to peak is a percentage difference between each peak." Yeah. So in any case, yeah, the definitions are about the same. So because we saw this sudden thing here, I went ahead and did an insulation resistance profile, and that's what it looked like. And that was with that AmProbe device. Would have seen something similar with, say, a PDMA, or there's a bunch of other guys out there that do similar. So then we did the, with the All-Test Pro, that would have been the 5. We did the low voltage test on the machine as well. There it is. And everything turned out okay. So between all of that, we had a good insulation system. Yeah, you don't always have to show bad stuff. I used to have people say, "Hey, do you have any pictures of good stuff?" Well, there you go. Vibration analysis on the same machine, slight, very, very slight stuff, but really everything was well within tolerance. And then an electrical signature analysis, same thing, unbelievably smooth. So at about 20, because those are 1800 RPM, no peaks on either side. If I had an unbalance or misalignment, I would see a peak here and a peak here at about 65 dB down. The noise floor is a little high. That has to do with a power quality issue in the site. Additional things we got from electrical signature analysis between all of that included all of our energy consumption. So this incoming power, that's the estimated shaft power. And then this is the air gap torque. Now, this particular technology, which is the empath, does some additional stuff now. Okay, so now let's take a look at a 13.2, 4,500 horsepower. That's the one that we saw being taken out. This was the problem. This is using chilled water through a radiator up here. It's called a TWAC, totally enclosed, basically cold water. You know, so everything's circulating inside. There's very little, there's actually some openings in here that allow moisture to ingress. It is Washington, D.C. area, so it tends to get very humid. And there was no valves to control the amount of water that went in there based on temperature. So it was constantly moving chilled water. So when we'd turn off the electric machine, you would hear it rain inside. So they had a couple of issues on one of the machines. One of them, you know, they had spent 6 weeks, everybody pointing fingers. They didn't want to pull this motor, and nobody would tell them what they were seeing. And I got a call to go in. It was my first trip out there, and discovered that it was, in fact, a insulation to ground issue on the rotor. A simple Megger test identified it, and I said, well, rotor's bad, motor has to come out. Apparently everybody was afraid to say that. So there was that. We also noticed when we were doing the visual inspection, so going in there, this is off of a flashlight, going down, looking and seeing that there was PD on the leads coming into the machine. That's what that looks like, the end of a cigar, that's PD, or partial discharge. We discovered some other things, like these leads, when they go out in the connection box, are all touching each other. So we detected evidence of PD on those as well. Surge test, you notice I'm using very low. It's a 13.2 kV. I don't like surge testing these. We were basically instructed to surge test these. So this would have been that first use I had of that instrument. And so we went out there and I had them sign off that it's okay. I had the leads lifted on the rotor, because whenever you have a wound rotor or you have a synchronous machine, if you surge test it, you're going to impress across into the opposite winding. And if you have the leads connected, it's going to go elsewhere. I was more concerned about the leads going into the shaft and then coming out and going into the winding. If they're close to each other and there's any issue whatsoever, it can arc. That did happen much later on. That was when the same engineer insisted that 27 kV was done on it. So we had him come down and operate the equipment. but that's another story. Low voltage test. This is what it looked like after it was repaired versus before. We had 6 of these machines, so went ahead and did comparisons. So those were the results. And then when we tested it initially, there was some signs of contamination, not a lot. That's insulation resistance. That's in gig ohms. And then here, this impulse here, we discovered it had to do with the leads, because when they took out the leads, which were originally an encapsulated tube, down the center of the shaft, that was all encapsulated, they left out the encapsulation. So with some moisture in there, we got a little bit of discharge at the end. This is another one that's Tom and forget the other guy. Anyways, when he pulls the cover off, this was their best motor. Let's see if I can. And if you can see it, I don't know if it's not running right now, but you can see there's steam coming out of it. That steam is because, and this was the reading after we dried the rotor, it was actually worse beforehand. And then it went right back to it. It started degrading, the resistance went down, discharges occurring across the whole length. Not huge, but identifying potential issue. We also identified something else because we had Basler units put in. Instead of the starting system they did have, when we pulled the data off there, they had basically 100 volts being impressed across that winding. Okay, so what did inductance reduce 50% after repair? Oh, that would have had to do, you mean here? That would have had to do with the fact that they had basically a direct ground and had lost part of the circuit. And they also had some other issues such as shorts inside the rotor. So when we put everything back in, we had switched over to Basler units. I convinced them to put Baslers in, and we discovered they had 100 volt sine wave going into the DC equipment that was causing some problems. So we had somebody come out and tune them, because you have to tune them. Here, where this found settings, field voltage was oscillating 100 volts, and then we got rid of it. Now, so once we identified all that issue, then we had fewer problems. Problems we primarily had with those systems afterwards had more to do with the prior repair process. We moved that to a different repair shop, and most of that went away. So getting into this, this one was an interesting case study. This one did do an RCFA as well. It was an interesting one. It was a large machine. It was delivered to a nuclear power plant, and it luckily wasn't a safety motor, but they had it for about 18 months. They were going back and forth with the OEM and pointing fingers at each other and everything else. They saw a large phase unbalance. This is a Megger DX. So you can see DC resistance 89 ohms, 89 milliohms, and 93 milliohms per phase. The impedance you can see as well, a jump there. And then inductance, slightly different, not huge numbers, and all in one phase. So this one had 514 coils. What was it? Seven circuits in parallel. So we went out and we started running down a list what the possibilities were. As part of an RCFA, we said, okay, here's what can cause the unbalance, as the first step. Oh, I'm sorry, it was close to 3 years. So we were outside, beautiful area in South Korea. So we go in, testing performed, large unbalanced in one phase, low voltage testing and surge comparison both failed. it almost appeared as if one of the 7 parallel circuits was out of the circuit. Now, because of my schedule and everything, I had a half a day to do testing. I flew in the day before, was brought down from almost down to Busan, but brought down from Incheon, and then the next day I had to, the later part of the day I had to go back to the train station, and then the following morning go back to take a flight. So I was one day on site, one day flight out, day flight back. So fun 12 hours of, 24 hours of flying in 3 days. But the high-speed rail was cool. So low voltage testing and surge testing appeared as if that no smoking gun was readily apparent. We went in, we loosened and tightened all the connections, everything else. Manufacturer's rep kept telling us from the factory, just run it, it'll be fine. But they couldn't put their protection in place because they had a phase unbalance, massive phase unbalance. So I get into a vehicle and they're taking me back to the hotel near the train station, and I'm reading through, and I see something that catches my eye about a bad coil, but it's very cryptic. So it's there in the report, but it doesn't give me any details. So the machine was large enough, we sent somebody into the machine to take some pictures. So I'm in the car and I get, this is one of the pictures they sent me. So 7 parallel coils evenly spaced in one phase were cut out because one coil failed, and instead of rewinding the entire stator, because they VPI'd the whole stator, they just cut the coils out of one phase. Just because it's new does not mean it's good. Something looking deeper, visual inspection will reveal issues and maintain communications between the owner and the vendor. Part of the reason that it happened was this particular manufacturer was being bought by another manufacturer, and this would have been a major warranty recall issue. The engineers involved, I believe several of them were let go as a direct result of this. The company itself made a bid at NIH for the 30 megawatt cogen unit build from 24 to 30 megawatt that I was overseeing, and I threw their bid out. I said, no way, not if they do this. They spent their time trying to argue it. As soon as I caught them, then they admitted to it and said, it's normal practice for an OEM to cut coils out of a brand new stator. Well, there's no standard saying you can't do it, according to them. And I said, well, every standard I read says it's a temporary fix, because I've done this before. I've cut coils out in order to keep somebody running until their next shutdown, right? So they determined that that was perfectly fine for brand new stator, and literally said in writing that, well, we only warranty it for 5 years. So they were hoping that that would survive for 5 years, plus without protection at a nuclear power plant. That did not go well for them. So in the end, they ended up, lawyers got involved. There was a big lawsuit. I didn't even need to show up for that. They used my records and the data and the pictures and my RCFA report. So I did an RCFA report on this one, and basically went back and identified a lack of standards on this, lack of this and that, and some decision making. So oddball motor repair, let's see, what was this? Oh yeah, okay, so it's gonna be the same machine. I'm sorry, 4,500 horsepower, another one of these. Passed electrical and mechanical inspections, gradually increasing vibration on each startup. So we didn't quite know why. We went ahead and we started looking at the vibration data. We started gathering our evidence and tested the rotor. There were some insulation resistance issues, the discharging thing. There was an audible thumping sound. The vibration showed an increasing one-time RPM. First phase analysis identified a signature. It looked like a cocked bearing. And then all of a sudden it was 80 degrees out in phase across DE. So there was everything indicating that there was something going on with bearings and other conditions, et cetera. And then when we opened it up, because that's part of it, is you always want to do a visual inspection. Visual trumps everything else. And I saw powder in there and I'm going, what on earth is that powder? So we created a very complicated test device, which was the end of a broomstick, with the broom still on it, by the way, and reversed some electrical tape on there because I wanted to find out what this material was. And the only way to reach in there was to do this. It was hot as heck in there because we were only allowed to shut the machine down a short time. And we come out, we take a look at it, it had flecks of red paint and everything else in there. It was insulation material. So once we identified it as insulation material, then we spent time trying to find out where the insulation material was coming from, and we noted something. This air dam was supposed to be into the windings with a 1-inch gap between the rotor and here. Instead, we had an 1/8 of an inch gap between the air dam and this, enough that they notched out parts of the air dam so that they could take their the measurements on air gap. So, you know, originally we thought it was a loose coil or something. When we saw this and we saw it's, here's an area where it was scraping, that's where that material came from. And we compared it to the other ones. Then we basically went back and said, okay, here's the problem. This needs to be repaired. 2 machines came back this way. We went back and went all the way back to the manufacturer on the RCFA. I won't get into it because, wow. We had a spare motor built at the same time, which was perfect. And the exact same people did this, the exact same winders and everything else, but under the direction of a manager. And yeah, we won't get into that far. Okay, switch gear. This one here, to put this into perspective, another 13.8 piece of equipment this time. What's really kind of cool is G&W's cabinet kept all of this contained. Happened overnight one night. I was called in to do the RCFA. First time this occurred. When I was doing the RCFA, we discovered something like there was an electrician in there some months before who had tagged out this cabinet and had not and had gone into this cabinet and set his grounds, not realizing that this was still energized. There's a shadow, there's a brick wall, literally. There's between this, there's about 5 feet and a brick wall, has a shadow of the person on it. When they were brought in, he survived, he was fine. He was wearing the right equipment and everything, so minor injuries. They had to go in and clean it. They used contact cleaner on all the soot on all of the insulators. Now these are ceramic, and just to put it into perspective for how hot it got is these melted. That's melting not from the rubber, but that's melting from the ceramic. And once, like this one here, I brought one of those back. They gave me one of these as a thing, and I had it in the office for a bit until one day it fell over, cracked, and then all of the ceramic inside had turned to powder. So it was that hot, and then all this rubber stuff had dripped everywhere, and you can see arc holes in different spots from where it arced here. So they had an ungrounded, they had a high resistance grounding system with all the fuses blown. So they had an ungrounded system. They had basically a potential to arc here. We started discovering a lot of other things on the workmanship on the repair following the problem. And all it took was a capacitor to fail somewhere else in the circuit, and they ended up with a ground loop that continued until the utility tripped them offline when the 13.8 dropped down to 720 volts, which took about 1.5 minutes. Here's some of the damage. Like this one got so hot, you can see the bolts separated. So we went ahead and we started looking at the bolts. Here's the RCFA for it. So here's the case. And then we said, okay, improper settings, high ambient temperature, da, 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 da. So here's where all those questions are, ground system fault. And then as we identify what so this is a human root, latent root, and materials root. So we identified those, nothing was left. So contaminants on surfaces allowed tracking, check the insulators, arc flash between phases, additional ground faults which caused the circuit. And then on this side, grounding system issues, the relays didn't work, sizing of the equipment, that's because the equipment was way oversized. And then we discovered loose connections, detected with infrared and locked washer. This was interesting here. We detected it with infrared, but because the electricians, when they were doing infrared, the electricians involved, they would have the plant shut down and then do infrared. I'm just gonna leave that there. Weather information, we went back and got all the weather information so that we could compare and see what was going on that particular day, what would have driven it, nothing. There was nothing there that would have caused any kind of trouble. We did discover that they had been putting the Belleville washers on the other side here, leaving the actual nuts unlocked. So the nuts themselves were backing off and finally caused a loose spot as well, which generated heat. So either they were going to have the failure they had, or they were going to have a loose connection catastrophic failure at some time. Luckily, nobody was injured, but you can see it's all on the wrong side. And they had these facing the wrong way as well, but they were all on the wrong side. So as we go through, see, here's what's beneath each of those blocks is root cause, physical, any recommendation that's developed, etc. I did that in 2017. Okay, root cause detected with infrared, connections were excessively loose from primary cause of failure, information related infrared detecting connection issues was not available, but we were verbally informed that none existed. Well, because they couldn't produce anything, obviously none existed. Okay, so this was the root cause, and those are the recommendations. Oh yeah, and they reused the Belleville washers. You always need to use new ones. I learned that from another project. So that's, don't worry about that. That was from the course. Now let's get back to the wind thing real quick, and then we should be done here within the 5 minutes. So this is that winding failure. This is one of the reasons why we don't see a lot of the bearing failures anymore. They've insulated that. That is another subject from another thing that I just presented on, having to do with circulating currents up tower. It's going to be almost impossible to read this because this has been moved from time to time. I have to go find the original file. Winding failure, surge arrestor failure, or rotor failure, and then rotor winding, and then thermal conditions, et cetera. Here, partial discharge, and et cetera down here. So all this stems from insulation to ground fault. So we discovered a few things when we were taking it apart. This was a cold weather machine, hence the color from this particular manufacturer. The dark blue meant cold weather, but all of their plastic bits were not meant for minus 40. So they minus 40. So they were fracturing and breaking off. And then all of this rusty colored dust in here, that is remains of wedges. So that's all wedge material. So the magnetic wedges, as it turns out, okay, I don't have the picture. I put a magnet in there and picked up all this material. It's all ferrous material. There's a neat effect that occurs with ferrous materials. Are there any ready software for templates that you use for our CFA reports? No, I don't use templates, but the company, the company itself does have them. So it would be Reliability Center Incorporated. They're out of Richmond, Virginia. They do have those. So when we took it apart and we looked down through here, you can see all kinds of missing wedges, and you can see damage on the rotor from the material, basically sandblasting it, because the wedges were ground up in here. And we found certain things. So it's a magnetic wedge, and the failures all seem kind of happen in the middle. What we found and we got in here was a lot of buildup of that material. This is after it was cleaned, before we put it on the stripping machine and identify the failure point. So one of the things we do at that particular facility is we don't use a burnout oven. So we just warm up the material to get the windings out. This is a different stator, but this is another wind turbine. And we basically warm it up enough that we can lift the coils out. So we try to lift them out as intact as possible to do our investigation and our dissection. Before we pulled these out, we removed the wedges, that's all the scrap that's there, and took a measurement down the sides and found where there was still material, there was 40 thousandths of an inch per side that was clearance. There's supposed to be 10 thousandths. So that meant the coils were each individually loose in the slots. And as the fields engage with each other, they pull in radially towards and away from the rotor. And that motion there is what was beating the wedges out. Now, the prior suggestion was, oh, it's because the magnetic wedges are brittled and not keyed properly that they came out. But we weren't seeing that. Matter of fact, all of the manufacturers were having the same issue from that same time period, and it had to do with, manufacturing floor being given time limits to assemble a machine because of the massive number of turbines that were being built at the time. And that result ended up with these knocking the wedges out. Then the material would collect along the edge, and then there's an effect called magnetic termites, where the ferrous material will actually start to spin and drill its way into an insulation material. This is that spot. Those are my old steel toes. This is where the surface, the short to the surface and the edge of the corner right at that failure point. And then these are actually bits of the ferrous material at different layers eating its way in towards the coils. What we found is in a few spots, there'd be a bunch of them all layered together, and then there'd be areas where there was arcing faults because of it, the burn spots. So this is where we saw it, and then as we got in there, there's the rest of it. And that would, that was a contributor. So you can see the actual holes there, and that dark brown, that's the actual ferrous material eating its way into the insulation system. So primary issue, manufactured with coils loose in the slots, thermal shock, meaning thermal cycling, because they counted on the VPI process to hold in place, but because these things start and stop so often, it's a lot of thermal cycling. There's no, they're up in the air. There's the ambient temperature is air temperature. It's not on a heat sink on ground where it would maintain a specific temperature. See high vibration? No, they did not see high vibration. We did see, because the vibration transducers generally used up tower are really crappy and generally don't work. So that's where electrical signature analysis started picking up big time in the wind industry, because we can actually identify when the wedges are gone. Shows up as a number of stator slots times the RPM plus and minus the line frequency of the generator. Actually, line frequency, the output of the generator, is a whole science I have behind that. It's a little bit different. So let's get on to a different one. This is the wedge issue with the SA. So this one here, last one, and then we'll be done. I guess I'm going a little over 3 hours. So hopefully everybody's enjoying themselves. I see all but one stuck around. So this one has to do with why we're seeing certain problems, why we're seeing, this led into a whole other area of research. This started well before 2020. These are GE 1.5s in this case. And we went in and first thing is we started doing inrush studies to see what starting looks like. Now we've done other inrush studies on other towers. This I used for an IEEE paper. They're supposed to have a soft start on them, but really what ends up happening is a circuit breaker closes, the entire system, which is turning at full speed, sees full torque for the first 1 to 2 seconds, which is definitely an issue for some of the mechanical systems, and then it all kind of evens out. There is an inverter on these. So this is up tower. This is the empath mounted up tower to get the data. So that's 1 phase, 2 phase, and 3 phase. This is the output based upon the wind speed. So at about 3.5 meters per second, they'll allow the wind turbine to energize. And then it comes up and at about 12 meters per second, 11 to 12 meters per second, it's at full load. So this is where it sits in between those wind speeds. So we take the data and we zoom in, we look at in this case, 1.5 seconds of full torque. The other thing we get to see during that period is this. Number 5 is interesting. So we have these peaks here. This is the output frequency. This is the pulse frequency of the inverter for the rotor. So an inverter runs in parallel with the rotor. I think I'll have a picture here in a second. And then this is the second. What we discovered here later through another part of the team from H&N Wind, another engineer, we were able to determine that is a resonance associated with the transformer. So we're seeing a transformer resonance that's a direct result of a bunch of other stuff. This led to work that we completed on gassing in these types of turbines in the oil-filled transformers. So, and then it doesn't really settle down. I think that probably end up showing a video. This is the rotor circuit. That's just garbage. Not anything you can do with that. If you can see this is real time. This is the actual reading refreshed every fraction of a second. And you can see that's all steady. The other thing we noticed here was during that startup, we have the impulses and everything. And then as it comes up, the air gap torque increases as the load comes up. That was very interesting, especially when we started looking at what those frequencies were. And we're able to pull out that those frequencies are coming back from the grid back to the wind turbines. So they're causing a subsynchronous resonance in the air gap of the machine. And that subsynchronous magnetic resonance was causing fatiguing of all the Y rings and all the components. That's the fatiguing here of an unfailed portion of a Y ring that failed. So that fatiguing was causing them to break, usually right about where they were annealed, because they were brazed in place. So the heat would anneal it, and then there would be a fine line where it was hardened versus soft. And that movement and all the flexion due to the constantly changing magnetic field fatigued that ring, and then they start to fracture. Every single doubly fed induction generator on the planet is going to fail the same way. This is the circuit for 96% of all land-based wind turbines. So we have a direct output all the way to the transformer and out to the grid. Depending on where you are, depends on what the output of this is. These are generally 690 volts, but could be 575, 480, and some we've seen as high as 1,000. There are some 6 kV and 12.4 kV machines out there. They're rare. And there's a couple of 13.8s. There's 10 of those at YCAN, which is in Prince Edward Island in Canada. And then there's a couple of sites here. Most of them have been retired in the States of an actual Type 5 wind turbine. Those are synchronous turbines. So the speed of this generator can be several. They could go from, if it's a 6-pole machine, it can go from 1155 up to 1440 RPM. And then what you do is you control the air gap speed with the inverter. So you get a constant output speed. Primarily, these were designed originally around 50 hertz, so we change them here to 60 hertz in the US. So how far do we step back when we start looking at that study? At the turbine, groups of turbines, whole site, operating area? Well, actually, we look at the whole thing. So in this case, we had to take a huge step back and look and see what the grid impact was. And the direct result is we have a strong idea. We're hoping that there's different types of controls. These are old towers that use what's called grid following, meaning the output frequency and voltage depends on what's present on the line. So it kind of follows along. The new control type they're talking about, because a larger percentage of the energy produced in certain areas will come from these, and we don't have the actual large rotor inertia that you would in a larger generator. So they're creating what are called grid forming controls. So I talk about them, but they haven't really been applied yet. We're trying to determine if those are going to cause more failures to occur or if they're going to eliminate this particular failure defect. So real quick, because I promised it, and we will be done in about 5 minutes. I'm going to show you a little bit. And by the way, panhandle wind. When I show pictures of turbines, they're not other people's pictures. Okay, so let's say I have an electric motor driving an inline fan with belts functionally failed, meaning it stopped working. Did it mechanically fail or did it electrically fail? You can see I don't have anything there yet. So here, is it a bearing failure? Nope. And then don't know. So nothing there yet. So it's still a hypothesis. Mechanically failed, shaft failure. So this, if I remember right, this would have been an annealing oven issue. This I just happened to be on the computer. So where I end up here is, did it electrically fail? Well, what are the hypotheses? And this is where the data comes in. So I can say, did it electrically fail? Insulation to ground. I'm just going to do okay. And I set a confidence level to say, am I confident? So 5 would be, yep, it's absolutely, I'm 100% sure. 1 would be, probably not. So when I click OK, I come down here, double click on it, and then I can come in and say, what are my verification methods? Yeah, there we go. So verification method, insulation. Okay, need greater than 100 megohms at 1,000 volts. I'm just making stuff up. So let's say I do that. So then I will save that. And then I can come in and say, we went ahead and insulation resistance was 1 megohm. Failed. Or I don't have to put down failed, just put in what it really was. I can have links to files with images of that result or PDF of the test result. Save that. And then when I come here, then I can say, okay, it's a physical root, human root, latent root. Mark is not true. but it's true, it is an insulation to ground fault, but I'm not really done yet. So I'm going to put in another hypothesis and say, now I might have a branch of it, contamination. And there we go. And then let's say I filled out the verification. Now let's go ahead and we'll just put it in. I can put in multiple verification methods, by the way, visually. Okay. And then here, full of contamination, full of water. Okay, or whatever. I go there, and then I have that, and then I can say, okay, now I should continue, but just for our purposes here, I'm going to say that's actually that's not a physical route. That is going to be a latent route. There we go. And then that's it. So now I have that as a record. I can come in and eventually communicate that. Put in any summaries, put in any recommendations here. So I would come up here, summary of findings, recommendations. Oh, okay, I didn't put down a cause. So I'd select a cause. It would identify what type it was, and then I could put down, what my thoughts were. So let's go ahead and add one. Oh, there it is. Contamination, latent, who's responsible, proposed, cross, it's going to take, how many ever hours, remove and have motor cleaned, or something like that. And then, and whatever level of detail, I can even put a spec in if I want and have it attached or whatever else. Once I'm done, then I'm done with that, and I can go to the report. Company information, save the report, put in any footers and headers, and then if I communicate the report, it's going to generate it's not going to be perfect because I haven't put anything in this. I haven't used it on this computer. I can tell it what I want on here, motor go boom. And logos and whatever else I want to put on there. So now it's going to generate this report as a PDF for me, and that's basically the system in a nutshell. I went through pretty quick on this stuff. Let's see if I can do the pages. Oh, it's gonna old software. So there's data collection stuff, my evidence, the analysis, the verification logs, all the other stuff. And then when I do a report, this will be one of the attachments, and I'll have a summary up front that I write separately on letterhead, a description of different things we found in that write-up, and then I'll attach this on back as the step-by-step, showing the thought process of what we did. And that should include, I don't know if I did it for this, if I checked it. Yeah, somewhere in there should be the chart. Oh, somewhere in there. That's kind of it. Any questions? See, we've lost a few more people. Let's get down here. No. Okay. And with that, if you have any other questions, let me know. Yes, there will be a recorded version of this out. I'll be sending that to all attendees. Those who stuck around for the whole thing, which appears to be most of you, will receive a certificate, usually within 1 to 2 days. If you don't, let me know. They're automatically generated from GoToMeeting for me. And with that, have a great day. And by the way, happy 4th for those of you in the US. Let's see if I can remember how to turn this off.